Sure. Hey.
तो हमारे सर ही आएंगे ना।
Folks, as you enter, if you would please take the seats on the center, because we have plenty of seats open there. It will really help the meeting.
Hi, good morning, Dr. Chowdhury. Let me just leave the Zoom session for the AV folks. Could you please confirm in the chat that you can hear me? Perfect, awesome. I'm just going to leave the meeting. Hi, Dr. Chowdhury. Would you mind testing your AV with us?
Yeah, of course. Hi, testing, testing. Can you hear me?
Yeah. Can everybody hear Dr. Chowdhury? Awesome, thanks, we can. Would you mind sharing your screen as well so we can test that out?
Yeah, also, here we are. Says loading.
Yep, it's,
There it is.
yes.
Here we are.
Yep, this works. Yeah, I think we're good. So
Magic of technology.
yeah, I couldn't agree more. All right, let's see. The time's 8:59. We'll start at 9. Can the AV folks confirm the video is live streaming? Okay, perfect. Is the video live streaming, Gareth?
Can we share the screen from the far end?
Would you mind? Oh, okay. Would you mind sharing your screen again, Dr. Chowdhury? Let's make sure the live stream is okay.
Is that working? It says it's sharing.
Okay, I think that works. So let's just get started. So hello, everybody. Welcome to the third keynote of JuliaCon. Before I introduce Dr. Chowdhury, I just want to request everybody to keep the questions towards the end because this is a Zoom session. Once you ask the questions, I'll repeat this on the microphone so that Dr. Chowdhury can hear us, and then Dr. Chowdhury will answer the questions. Okay, on that note, I'd like to welcome Dr. Ruman Chowdhury to JuliaCon. Dr. Chowdhury currently runs Parity Consulting, Parity Responsible Innovation Fund, and is a Responsible AI Fellow at the Berkman Klein Center for Internet and Society at Harvard University. She's also a research affiliate at the Minderoo Center for Democracy and Technology at Cambridge University and a visiting researcher at the NYU Tandon School of Engineering. Her passion lies at the intersection of artificial intelligence and humanity. She's a pioneer in the field of applied algorithmic ethics, creating cutting-edge socio-technical solutions for ethical, explainable, and transparent AI. She is also an active contributor to discourse around responsible technology with bylines in The Athletic, Forbes, Harvard Business Review, Sloan Management Review, MIT Technology Review, and VentureBeat. Let's all give a round of applause and welcome Dr. Chowdhury.
Thank you for the introduction. I can't hear the audience, so I hope it wasn't completely silent on your end. Good morning, Cambridge, and good morning, JuliaCon. I really wish I could be there in person with you. Ignore my Harvard affiliation. Actually, MIT is the place where I got started. So I wish I could be there with you all. From everything I've heard, it's been a phenomenal conference, and I'm honored to be your third keynote. So let me start sharing my screen. All right. So the other thing I'm doing lately is I'm the CEO and co-founder of a nonprofit called Humane Intelligence. And Humane Intelligence is democratizing red teaming. And what we're doing is bringing the art of algorithmic critique to a broader audience than just a small group of people. And my talk today is about building responsible AI in the age of generative AI. We've already had an introduction to me, but just sort of a little bit of maybe a slightly different perspective about myself. I'm a data scientist and a quantitative social scientist. I've been building responsible AI solutions since 2017, so I got my start as Accenture's first global lead for responsible AI. I left to start my own company, Parity AI, and I was acqui-hired over into Twitter. We all pretty much know what happened last November, and if you don't know what happened last November, good for you, and I hope you keep your rose-tinted glasses on. But what I'm working on are currently algorithmic audits, policy, and algorithmic accountability. So in general, my passion is in developing intelligent and smart technical approaches to identifying issues in algorithmic solutions and also fixing them. So this is what the last 5-ish years of responsible AI has looked like. So like I said, I got my start around 2017. Of course, plenty of people predated folks like myself, primarily in research, although in application, that was kind of when it picked up. And I was one of the first people in the world, really, to be focused on developing solutions in responsible AI. And at that time, nobody really knew or cared who we were, what we did, and everybody thought all of our work was philosophical. So in 2017, we'd get these questions on all these panels we'd be on or talks like this, and people would inevitably ask, is AI alive? Is it going to take over the world? Are we getting, at that time it was like paperclip maximizers and trolley problems. And I used to have a slide at the beginning of my talks, and it would say there are 3 things I don't talk about. I don't talk about Terminator, I don't talk about HAL, and I don't talk about Silicon Valley entrepreneurs saving the world. Ironically, the photo I used for that, and I literally am not kidding, is a picture of Elon Musk in an Iron Man outfit. It's as if I read my own future. The next wave of narratives were about whether something X will be replaced by AI. At that time, actually, most of the conversation was around factory workers. This idea that robotic automation, and in consultant speak, it's usually RPA, robotic process automation, would replace factory workers, would replace construction workers, et cetera. And it was largely a conversation about actually blue-collar jobs, which was interesting. Fortunately, those of us who are working in the field shifted the narrative away from is AI alive or will it be alive to like, hey, realize that AI bias is actually societal bias. It is reflecting the issues that exist in the data, which is a reflection of the issues that exist in society. It could also be a measurement issue, operationalization. There are many ways in which issues may happen, but it is not because the AI is alive and deciding to do bad things. Thank goodness we got there. Then we entered the world of actually starting to create solutions, and around this time is when I left to make my startup. This idea of measurement, quantification, trying to develop approaches to have applied conversations on how to, let's say, develop risk methodologies or ways of approaching harms. And then we were talking about developing a regulatory ecosystem. So this was around the summer of last year, which seems like another lifetime because at that time I had my amazing team at Twitter, which was an applied research and engineering team. I was actually building out a red team as well and hiring for those roles. And many folks were realizing that, hey, it takes a village. There are many different kinds of roles that are required to solve the big issues of solving for responsible AI, or at least working towards responsible AI. And then generative AI hit. And here we are again with these conversations of, is AI alive? And will everything we do be replaced by AI? So I want to talk a bit about what's new and what's not new, because I think there is a lot of revisiting old narratives by new people. And of course, I don't want to dampen enthusiasm, but I also want to bring in the prior wisdom so that we don't reinvent the wheel, or worse, redo the issues of yesteryear. So first is, generative AI, in my opinion, has actually been a revolution in accessibility of AI systems. So why is it GPT 3.5 that caught everybody's imagination? Why are LLMs or chatbot, why is this a big conversation now? GPT has existed for a while. Same thing with image generation. We've had the ability to make images for a very long time. Even deepfake generation hasn't existed for a very long time. My first visit to DEF CON was in 2018. In 2018, one of the talks, the panels I was on, was with Ari Herbert-Foss, Sam Cole, and it was about deepfake pornography and deepfake generation. So this has been around for a while. What has changed? Well, first, it's that all of this is part of an increasing no-code or low-code revolution. And it's been really fascinating to see the accessibility of it really change people's mindsets about what AI is and what it can be bringing to them. But also, on the other end, it is bringing the same old narratives again. And again, it is not necessarily because the technology is so much more improved. It is improved, but I think a technical person sees how it's improved. To the average layperson, it's the fact that one can, quote, converse with an AI system in a way in which you would text your friend, your sister, your brother, that makes people think it is alive or it is somehow talking to them. But interestingly, this accessibility is aligned with the culture of data science, and so one of the reasons I'm happy to be at JuliaCon, albeit remotely, because the culture of accessibility is actually the culture of communities like the Julia community. So what's old? As I've said, we've somehow rewound time to 2017. We're having these same conversations again, right? So the idea that there's embedded biases and issues in these models. It didn't go away just because they got fancier. It didn't go away because we had more parameters, and it did not go away because we are now consuming an insane amount of data to build them, and it certainly did not go away simply because we've created more accessible interfaces. If anything, the creation of more accessible interfaces has actually led to more and more people experiencing these harms, because these broader use or general purpose artificial intelligence models, you really can't make them bulletproof to every kind of adverse event that could possibly happen. So what's changed? Here's where I speak a little bit more optimistically. One is that we are no longer in the early days of AI. So this technology is widespread. We have had years of conversation about it. We have had years of talking about harms, biases, etc. Everybody who has been engaged in this field is smarter. We now have teams capable of at-scale deployment, but also we're smarter about the impacts of these systems. So now we have laws or bills that actually address impact in my humble opinion, a smarter way. We have the NIST AI Risk Management Framework. We have the European Union's Digital Services Act. We have the EU AI Act. And for example, we have local laws like Illinois biometric privacy, as well as insurance laws in Colorado that are actually specifically targeting adverse events and also disparate impact. So what's not changed? What's not actually changed is the culture and community of the people who have built this technology. So I'm speaking as a data scientist. I know everybody in the room may not be a data scientist, but our culture is actually the same. So we thrive on a culture of collaboration, community, open source, and open access. And it's really fascinating to see the conversation about the impact of open source now become mainstream. And it is actually kind of funny for me to see people reacting to the concept of open source as if it is some sort of crazy free-for-all community of people who just do awful things in the world, when actually some of the ways we have educated, we've shared our knowledge, and built some of the best solutions in the world relies on this collaboration, community, open source, and open access. So why is culture important? I want to talk a bit about, one of my bullet points at the very beginning was about needing a regulatory ecosystem. And I'm going to expand the notion of what people think of when they say regulation or governance. I think people think of a very traditional adversarial environment, one in which people are just trying to build stuff, and then kind of the annoying compliance people come in and they wag their fingers at them. They sort of tell them what not to do. But that is actually not how anything is built well. So culture is incredibly important because culture is actually the only way in which we make anything happen. During my time at MIT, actually, I had this really great professor, visiting professor from Amherst. His name was Austin Sarah, and this was a class about the rule of law. And he said something that really impressed upon me, and he said the rule of law exists when people stop at a red light in the middle of the night. So the point of having laws is not for people to live in a surveillance state where they get punished whenever they do anything. The rule of law actually exists when we understand that it is our responsibility to contribute to a community, and that our responsibility is to ensure that community is healthy. So culture is important because there has been sometimes a culture of moral outsourcing in data science, in the engineering community, and in big tech writ large. This idea that artificial intelligence and these programs that we're building are somehow independently making decisions, and as a result, it's not our fault if what we build is doing bad things. And you see that reflected in the language. So I have a longer talk on moral outsourcing that I do, where I talk about how the linguistic choices to say AI, AI discriminates against Black people, or AI causes X number of people to lose their jobs. Will AI replace teachers? These are all headlines that we read. We've never actually spoken about another technology in that way. We've never talked about a technology as if it is taking the action rather than people creating a technology that then takes action. I understand that there is a slippery slope where, it is by a layperson appearances making, quote, independent decisions, but I also think sometimes the tech community is a little bit disingenuous in letting people think that these things are more capable than they are. Again, the problem with that is moral outsourcing. By dumping the responsibility of the action on the technology, then we get to wipe our hands clean and say, well, I'm just the engineer, I just built it. So culture is also important because it starts to build accountability into practice. So it creates the norms in our communities that say, don't share data irresponsibly, don't scrape the internet for personal and private information and use it to train your models, don't create malicious large language models or whatever it is. And it actually enforces that without people having to come and find somebody or bring in the government, et cetera, to do it. Of course, it is important to have regulation, but actually all of that will fall apart unless we have the basic building blocks, again, building on the culture of collaboration and sharing and openness that is part of broader communities like the Julia community. So there's tensions, of course, but there's also benefits to creating a good culture. And this is why, historically, when people say that, we need a Hippocratic oath for data scientists, it's actually not something that I think will work. Because our community is not built on strong indoctrination, sending people to programs, having them do extensive shadowing or interns or residencies. So Hippocratic Oath exists for fields like medicine, where you spend years being indoctrinated into a culture, very specifically. If you have any doctor friends, that is actually what your residency is teaching you how to be a doctor by shadowing doctors and being taught what a culture of being a medical professional is. The Hippocratic Oath is simply a manifestation of all of their training to date. It is not a spell that magically makes you ethical. So a Hippocratic oath for data scientists, a Hippocratic oath for engineers really only exists if you've had a culture that has taught you that this is important. So where does that leave us? So first is that the toys have changed, but the rules of the game have not. Second is that algorithmic bias still manifests itself in the same ways. And third is that you need a full ecosystem approach to addressing responsible AI. So culture, creating the right culture is part of what I put into independent third parties, right? Providing external review and accountability. And this is a very, very broad spectrum. This is everything from I manage a GitHub repo where I share code and I'm going to institute guidance for how people should use what I'm building, all the way to I am an algorithmic auditor who actually runs a consultancy and I exist independent of tech companies and government, but that is independent groups. And independent groups are actually some of the most underfunded, undersupported, and least understood. We have industry, right? And the role of industry is to equip talented and resourced internal teams to address these issues. And I can tell you from personal experience, no industry team alone can do this. All industry teams rely on external parties and government to give them guidance, all good ones at least. The best industry teams recognize that we need people on the outside to give us information, to provide objective review, and frankly, to do some of the things that we don't have time to do. Because if you are working at a company, you are building solutions towards improving that company's product. It is not actually your job, in my opinion, when you work for a company, to be part of an independent review. It is your job, however, to support those people and provide them information and resources as best you can, given the resources that you have, which tend to be sometimes time, because it's your job to do this work, and often it is something like data, access, information, etc. And then, of course, there's government, creating standards, guidelines, benchmarks, and laws. So I want to talk a bit about what government's doing. So I talked a little bit about independent parties, and we'll get back to that. Talk a bit about what government's doing. So regulation is here, and it's very exciting. And every time I have this slide or give this talk, I say, I never thought I'd be a person that would say regulation is exciting, but regulation is very exciting right now. It is opening up new possibilities for auditing algorithms and reimagining AI risk detection to be more inclusive. So specifically, if you look at the language of things like the Digital Services Act, what it is not saying is we need to make sure that your data set is being stored in some sort of a compliant way, et cetera. It is actually saying, companies, you have to prove that your models are not violating basic fundamental human rights, that they are not subverting free and fair elections and democratic processes, that they are not promoting gender-based violence or causing adverse harm to young people and individuals online. And it is really critically important that we understand these systems holistically, and systems being defined not just as the code, but also as the documentation, the people, and the individuals building the tech. And that, to me, is actually incredibly exciting. But then that raises a question, what is an algorithmic audit and who is an auditor? And that's a really good question, and nobody knows the answer to that. Folks like myself are trying to work on it. There are a lot of people out there who have written very technical papers and lots of technical approaches to algorithmic auditing. None of this has been codified into laws. So any of these laws that say things like you need to audit an algorithm based on impact on fundamental human rights has not actually laid out how said audit should occur. And that's actually a pretty big gap, or I suppose one could say a pretty big opportunity if done well. And this is the one of the many things lately that keep me up at night, where I hope that the way this field trends is actually towards improving the training and skill set of smart people to be able to critically analyze models. And this is why I'm such a proponent, and now that I'm on the outside, really trying to build up capabilities in independent groups. And again, this is everything from people who are creating the culture of what it means to build and share code, all the way to people who are trying to build full-time jobs in auditing industry models. So what I'm focused on are things like upskilling and training, institutional access gaps, investment in tech, and then balancing accountability and transparency, which, if we have time, I can talk a little bit about the kind of work I'm doing there. So laws like the Digital Services Act and the Platform Accountability and Transparency Act, PATA is a bill right now, would require auditor access to things like A/B testing platforms and technical inspection. That has never actually been granted before, which is great, but also, again, very, very scary. So how can independent parties be engaged? So So in 2021, my team at Twitter launched the first algorithmic bias bounty. There was kind of a lot of talk about it, and nobody really understood what we were doing. I don't know if we entirely understood what we were doing, but we thought it would be kind of cool to actually allow people access to one of our machine learning models. And in particular, it was our image cropping model, which was the same model that the previous October people on Twitter had pointed out seemed to be cropping people in a discriminatory fashion, where it seemed to favor light-skinned faces, and some people were actually saying it was cropping women in a way that was not that was quite sexist. My team actually conducted the algorithmic audit. This was Tao and Kira with help from Shubhanshu, who was on another team. We published our findings. We realized it wasn't enough. I mean, we tested for the very specific things people were critiquing for, but there were many ways in which bias could creep itself into an image testing model. So we opened the first algorithmic bias bounty. We shared our code. We created a rubric, and we were really impressed at the kinds of responses we got, not just ranging in the creativity of solutions, but also the creativity of approaches. And that was one of the first times I saw citizen data science at its best, where somebody who actually didn't know how to code was one of our winners. And this individual simply dropped pixels into images and posted them on an alt Twitter account and demonstrated that they could shift where the image cropping algorithm was shifting simply by dropping a pixel into an image, which I thought was incredibly creative. Last year, I established the first nonprofit dedicated to algorithmic bias bounties, and that work persists today. So last fall, we did a technical challenge. We launched it at a conference called CAMLS, which is about AI security, lowercase s security, and lowercase s safety. We're not in the world of capital S, if you know what I mean. And in that, we created a competition for technical folks building models to think about different ways in which to optimize the output of their models, to not simply be around R squareds or accuracy. And that work continues today. So in my congressional testimony a couple of weeks ago, I am literally the only woman, and actually I have to date been one of only 2 women who have testified in the latest round of congressional testimonies, which is pretty unfortunate given how many women have built this field of responsible AI. But here's what I emphasized. First, I talked about support for AI model access to enable independent research and audit. Second is investment in and specifically legal protections for independent red teaming and ethical hacking. So again, this community of people outside of industry and outside of government who would be allowed the capacity and capability to audit and find issues in models built by industry. Third, the development of a technology oversight body to supplement existing efforts. And then fourth, the development of and participation in a global AI governance organization. So I'll kind of not talk about the last 2 bullet points because that's other stuff I'm working on, and actually really focus more on the first 2. So again, communities like the Julia community are critically important to maintain the independence of people who are smart and who are capable and who really want to build all of these solutions to improve what's happening in the world. We're not just here to make profit for companies. We should also be here to ensure these technologies are used in ways that are actually beneficial to people. And second, part of that actually is legal protections for folks to be critical about the models that are being built by tech companies. And I'm drawing from the InfoSec community and their history of actually being stifled by companies when folks in their community have demonstrated incredibly harmful and insecure ways people's data has been stored or code has been developed. And this is sort of culminating an event that's happening in, I think, a week and a half, which is actually one of the reasons why I can't be there in person with you today. DEF CON has sort of taken over my life in the best way possible. So myself, Sven Cattell, who is the organizer and founder of the AI Village at DEF CON, and Austin Carson, who's the founder of a nonprofit called Seed AI, as well as literally at this point an army of people are all volunteers, actually, all of us included, have actually managed to corral every single large language model company. I say corral lovingly and jokingly because actually companies have been really enthusiastic partners in helping us design this challenge. This challenge is also sponsored by the White House, so we're working with the Office of Science, Technology, and Policy, as well as NIST, and also a couple of nonprofits that are focused on impact of technology in society, and also have some expertise in developing red teaming. And we will be hosting the largest ever generative AI red teaming exercise at DEF CON 31 in, like I said, about a week and a half. We are hoping to bring thousands of people in front of large language models. And my nonprofit, Human Intelligence, is in charge of designing the actual competition. So this an interesting thing we're doing here. We're expanding the notion of what it means to red team from a traditional security perspective, which is specifically around hacking and malicious actors, to bring in what I call embedded harm. So creating challenges around people surfacing actual harms that occur in these machine learning and in these AI models organically, rather than tricking it to do so. So we have challenges designed around societal bias, information integrity, internal consistency, multilingual harms, but also things like prompt hacking and security. So we're forging new territory. First, we're creating institutional pathways to escalate harms. We're learning from the expertise in cybersecurity, and AI security, and again, lowercase s security, is sort of its own hybrid. We're partnering with corporations, government, independent third parties, and we're also creating pathways for underrepresented communities with a sponsorship from the Knight Foundation. Seed AI is able to bring in hundreds of community college students to be part of this challenges competition. Again, the goal of all this work is to open up what it means to be a critical thinker about tech and recognize that you don't just have to have a CS degree to do so. And what we're collecting are at-scale data about harms, and then research into how hackers hack. We have researchers coming from MIT and Harvard to really understand the mentality of how red teaming works. And then afterwards, what we're trying to do is create a space for people to be independent of institutional affiliations in order to participate, and also be more inclusive by bringing these challenges to a broader community. So I'm trying to wrap up so we have time for questions. How do we build responsible AI in the age of generative AI? So algorithmic auditing is actually not a new thing. Data science programming has always been around the thoughtful selection of the appropriate tools for a task. And algorithmic auditing is about assessing the appropriateness of these tools and if they perform the task at hand. It's about understanding the mathematical limitations of the models and the decisions being made. It's about designing interventions and best practices. And it's actually also about measurement and assessment, which again, if you're somebody who likes breaking things, and if you're somebody who also likes building things and fixing things that are broken, this is actually the field for you. And also we're getting there by going back to first principles. We have always been about problem solving. Our problems have never been build a product, but actually build a product that benefits society. And we determine this optimized outcome empirically through qualitative and quantitative data. In other words, it is our job to prove that what we've built is doing its job. And this is not just through optimization of quantifiable things, but also by just opening our eyes and looking around in the world. We have the smartest technical minds in the room, but they're not always enough. For models that work at scale, we need non-exploitative at-scale solutions to address harms. We need a spectrum of accountability, and we need more voices that provide structured feedback, and we have and make sure we have companies accountable for identified harms. And if you are interested in the red teaming exercise we're doing at DEF CON, it's in Vegas, August 10th through 13th, and our website is www.airedteam.org. We have a couple of blog posts up that sort of are informative about what we're doing and how we're thinking about it by everybody involved. And thank you for your time.
Can you hear me, Dr. Chowdhury?
Yeah.
Oh, perfect, awesome. Thank you so much. That was a wonderful talk. Questions. We have plenty of time for questions. So you'll have to tell me the question here. I'll have to repeat it on the microphone. So, yes.
Thank you for your talk, Dr. Chowdhury. Would you happen to know what some of the greatest harms to non-English speakers are from generative AIs? Because a lot of the research that goes into it is mostly focused in English.
So the question was, what are the greatest harms from generative AI to non-English languages?
Oh, that's like, what a great question. And interestingly, so every week I host a design committee meeting, which is actually one representative from each of the companies, one representative from each of our White House sponsors and our nonprofit sponsors. And multilingual harms has actually been something that the companies have been the most interested in. Most of the trust and safety mechanisms that are built for these language models are actually built around English. So it is actually quite easy to get models in a different language to do things that they can't do in English. And it's simply a problem of tackling of scale. It's the problem of finding multilingual trust and safety folks who would be able to tackle every single problem that we have identified in English and also reproduce them in everything from Farsi to Turkish to Bengali to Japanese, etc. So you can imagine how big of a problem that is to tackle. It is a near insurmountable problem. And again, only a problem that can be well solved by humans. And this is why it's just been the topic of a lot of interest. Most of the language models that are out there, they have very careful language, and understandably so, about how they are optimized for English, and they only suggest building commercial applications in English, and that is why. I think Roya Paksad, who's the founder of Taraz, who's also on our design committee, has actually shared some of her experiences in red teaming in Farsi, where it's quite easy to get the model to, let's say, create insensitive jokes about your disabled Muslim friend in a way it would not in English, or to create to give you code to do a race and gender classifier that assesses the value of an individual based on a photo you've given them. And again, so most of it is really just about embedded harms. It's also about the lack of trust and safety protocols and protections in the way they exist in English.
Yes.
So I think one of the things that I think about is like when you have like cases where algorithms are not able to like perfectly identify marginalized communities or like kind of like for example or whatever. A lot of that is like it seems like a data insufficiency problem, and it seems like there's an additional ethical consideration where you're like, okay, well now we have to like, if we want to like kind of, it seems to me that the obvious way to like reduce a lot of bias in like these models or a natural conclusion someone might make is to just collect more data on marginalized communities in the natural context. But that seems very weird to me. I don't know if you could comment on that.
So the question was, in many cases, these algorithms don't end up identifying, let's say in case of image image classification, they don't identify folks from marginalized communities. This seems like a data insufficiency problem. One obvious way to counter that could be to collect more data on these marginalized communities, but that raises a secondary ethical concern. So that was the sort of question.
Yeah, so thank you for literally wrapping the entire conundrum in a bow. So two thoughts on that. Sometimes it is a data insufficiency problem. With the image crop model, what's really interesting is the original model was the way the original algorithm worked. It was trained on human eye tracking data. So what they did, and it's interesting because all of this was actually an open source model that Twitter just used. What they did was stick people in front of a computer, they showed them a whole bunch of images, they tracked where their eyes went, and then they used that to say, oh, okay, these are the most popular places people are going to look in a photo. So it essentially created a heat map, and we have a whole explainer about that in the paper we've released. So when it was actually cropping, so what our research actually found was that our model preferred women and preferred younger women, and it preferred light-skinned younger women. And this was actually mostly because young white women are held as the pinnacle of beauty standards, and most things that are sold to us or showed to us as beautiful or things that are desirable are young white women. So human eye tracking naturally went to that. So that would not be solved by having more data. Another aspect of it, and again, one of our submissions was about disability, how differently abled people, specifically people in wheelchairs, would often be cropped out of photos because most people are standing and there's one person sort of lower down. Again, like having more pictures of people in wheelchairs wouldn't have solved that. So it's interesting, but yes, I think in some cases it is a data insufficiency problem. But to your second point, we have another paper that came out towards the end of our tenure at Twitter where we had attempted to identify race-based biases in our machine learning models, in particular our content recommendation models, because of people telling us that there was a sentiment that our models would not promote content from Black people as much as it would promote content from white people. The problem is we don't know what race anybody is, and frankly, Twitter shouldn't have that data. The best we could do is aggregate up to census tract level data, which is publicly available, and make the assumption that the distribution of people on Twitter would mirror the distribution by race of a census tract, which just isn't true, but it was the best we could do. And our findings were inconclusive. So you're right, it would be great to have some sort of repository of data that people could independently tap into, maybe hosted by a trusted third party. Some of that actually fed our work on privacy enhancing tech, which actually still is ongoing, just not at Twitter. If you look at the nonprofit Open Mind, if you're familiar with any of their work, folks actually, if Jahao Chen is there, he's at the conference today, he's also working with them as well. I've also been helping them, sort of map out what it might look like for algorithmic auditors to have access to data via privacy enhancing tech, which may allow a solution to what you're talking about. It is still very experimental technology. I always say it's like between the R and the D of R&D, it's like moved slightly beyond pure research, but we're not truly in scalable development yet, but we are getting over the line. And it's a pretty exciting time to be working on PTs to solve the exact problem you're talking about.
Okay. Okay, I'm running back and forth here. Oh, it's good for my cardio. The question was, ChatGPT recently, there's been some attention recently that ChatGPT degraded in performance, and this is due to censorship or lack thereof. So could you comment on that? And for a small startup, they might not have the resources to counter this, Okay, thank you.
Okay. Microphone has arrived, yay.
Yeah, yay, microphone. So, so could you comment on basically the role of censorship within making these large language models perform well? And how startups can in fact do that, sorry. And how startups with limited resources can address that too. Thank you, sorry.
Yes, no, it's totally fine. Well, you all are asking me all of my favorite questions, and thank you for such thoughtful questions. So there's two parts to your question. I'm going to address the second part first. So there was that whole memo floating around earlier this year, the moat memo, the memo that leaked from Google saying that there is no moat, that open source capabilities will actually catch up to these privately built capabilities like within 6 months to a year. It's actually something that somebody had told me, someone at Anthropic had told me in like January as well. They were like, I don't even understand why we're spending so much money doing this because open source is just going to catch up. In my testimony, I actually, in my written testimony as well, I talk about actually trust and safety as the moat. And this is learnings from working at a social media company. We kept hearing last year that anybody can build Twitter in a weekend. Sure, yeah, you can absolutely build some sort of a app thing where people are posting stuff in a weekend, 100%. It's a weekend project. What you can't build in a weekend is an entire community of trust and safety, people who are identifying, malicious actors, people like harassment, and not because you have an obligation to society, but because literally nobody will want to use your product. And you should do it because you feel an obligation to society, but also like as, let's say, profit-motivated actors, nobody wants to use your product if there's Nazis on said platform, unless it is a platform for Nazis, which those exist as well. what I'm getting at is like the moat actually is the ability to create language models that are consistent and reliable, because nobody wants to slap their brand name on a plugin if you don't know if it's going to literally give wrong information to people. And that kind of leads to the second part. And I appreciate you bringing this up. I worry quite a bit about the notion of erasure. So for example, you can talk to most large language models pretty extensively about heterosexual marriage. You can ask it about ceremonies around the world and what brides wear and what grooms wear, happily talk to you. If you engage too much on the concept of gay marriage, it will only give you basic platitudes. It will only just say high level, very nice, very safe things. And what I worry about is an erasure of the richness of culture that comes from minority groups, because people are so afraid of saying something offensive, or worse, actually it's to protect against people who are actively going in and trying to make it say and do malicious things, that the best answer people can come up with is to say, well, let's just only have it say nice things. So interestingly, we are trying to build challenges around that, this idea of erasure, or, it's almost like discrimination by overcompensation. It's problematic. I don't know if I know the answer to it. To your question about startups, I've been toying with this idea of, and actually it's part of the work I'm doing, not just as human intelligence, but also some work I'm doing with companies. I believe there's these two layers of trust and safety. There's one layer that's sort of like the first pass, that one would say a large language model company or generative AI company is truly responsible for. And this would be just the basics of things we all agree with. These language models should not just deny that the Holocaust occurred, because the Holocaust freaking occurred, right? It should not give incorrect information about very specific things. It shouldn't say that certain minority groups are less valuable than others. Then there's the second layer of trust and safety that I think will start to become the responsibility of the companies building plugins into the core models. And that's actually going to be pretty tough for companies to do. And I do agree, it's actually been a canonical problem of startups trying to build social media platforms for years. And this is actually why, you only have had a few social media platforms become very, very big. It's the same problem in dating apps also, right? So like anybody can make an app that connects people. You actually need to spend a lot of money ensuring that your dating app does not lead to somebody getting assaulted, or somebody being stalked, or people being sent inappropriate photos, et cetera. That is actually the harder part. So I don't know if I have a clear answer for you, other than to say it has been a problem for anybody making any sort of a platform environment, or frankly, any sort of a consumer-based environment where you're actually specifically working with people. And to be honest, that's why many startups that are successful are actually in the B2B space, because solving consumer problems is very, very expensive.
I have a question about copyright violation. What is the progress that has been made in the industry in preventing AI from generating output that violates copyright? Because I'm on the brunt end of that.
Question. Yeah, no, yes. Little to none. It's really hard to do. So it's almost like it's like a collective action problem, in the sense that models are trained on so many pieces of data. Right now, you would have to sort of demonstrate that your images somehow contributed to the performance of this model. But because there are like billions, trillions pieces of data, you really can't. Like your individual data, like trying to assess the value of your individual data is like trying to assess the value of an individual drop of water in the Pacific Ocean. However, in aggregate, the Pacific Ocean is comprised of many, many drops of water. It is literally the same thing with language models. So the difficulty here has been, how can any individual prove that their contribution was so immense that like clearly their stuff is being quote unquote stolen? But that's like the negative part of it. The positive part of it is, in the few times I've been to DC in the past month or so, it is the one thing that everybody is the most concerned about. And, one can speculate as to why. I think one of the things is that like it's something that policymakers and lawmakers can understand. They can grapple, like intellectual property law and copyright law. I will say that I have heard from a bunch of Congress people that this is something they're very interested in. It is also tied to some of the noise that's being made about antitrust law. And also, obviously, it's the core of what's driving the SAG-AFTRA strike as well as the Screenwriters Guild strike. I wish I could say there was a good answer for it. There is not. But clearly, back to like my first slide where I said people kept saying, oh, will AI replace X? Well, that X is possibly acting, screenwriting, creative development. And it is happening in such a way that is so nakedly exploitative that you just can't ignore it. So while there isn't a solution, I think it is becoming one of the biggest catalysts in DC that will lead to better protections for people.
I believe we have a few more questions, but we've run out of time. So let's thank the speaker again. So I do have a few announcements, Dr. Chowdhury. I think you're welcome to drop off the Zoom anytime. Bye-bye. Thank you. Well, that was quick. Anyway, so a few announcements. Most important announcement, today is picture day. So all of us will have to assemble at the lawns right outside the Strata Center at 12:30 sharp. 12:30 sharp. All of us are spread across 7 different rooms. Please rush to the Strata Center as soon as the session ends to the Strata lawn so we can take the picture quickly so everybody can go get their lunch. Very, very important. The session chairs will remind you, please show up for the group photo. Everyone's invited. The AC 60 folks as well will be there. So let's all take this group picture. Next announcement is whoever wants to volunteer for JuliaCon in the next few years, next year, more specifically, please find us at the registration desk. We are more than happy to tell you how things work, etc., etc. We would love for more people to be involved. And plus, if you want some extra cardio during JuliaCon, this is a good way. All right. The last thing is that if you have an opinion or if you'd like your institution to host JuliaCon next year, please get lunch with me and and anybody else who's interested tomorrow anytime during the lunch break. Just find me. I'll be getting lunch. Join me for lunch. Let's talk about where we should have JuliaCon next year. And yes, I know a few people have already spoken to me about that. So please, if you do have an opinion and you have an idea for where it should be, please come. And finally, ASC 60 is happening now. Please go check out their talks. We have a break until 10:30. I mean, during which you can get coffee and snacks and extra breakfast if you missed breakfast. But please do check out the ASC 60 talks. And otherwise, immediately after the break, we will do the morning session, and then we will take the group picture. All right, thank you. Yeah, maybe the year after. That would be pretty awesome. Where's the university? Salt Lake City. Salt Lake City? Okay, awesome.
Yeah, so it's a fantastic location. Right?
Oh, yeah, I've never been to Salt Lake City.
There's lots of outdoor things.
Yeah, try and get people to Stanford? Yeah, absolutely. How are people going to drive on the way? I don't give a shit. That's not my problem. Yeah, talk to me about it. No worries, but thank you for letting me know.
with the temporal dimension. So did you start with
Okay. Do we want to show UniBuilder? Do we want to show UniBuilder?
During the presentation.
I'm kidding. Because I have it open, so.
But I mean, we don't. we don't have the time. Did you return yourself? Was it
Yeah,
only-
20 minutes,
Okay.
more or less. It will probably be faster because when I talk,
Yeah.
it's going faster, but
So we're gonna connect Adrian, right?
yeah, we'll connect him. I'm going to. Okay, this is working. So let me try with the audio. Let's see. Okay, wait. Let me close my things first. Oh, we're live stream on YouTube. Yeah. Hey, Adrian. Adrian just told me. Okay, so let me just close this thing.
Yeah, because the microphone is
Okay. Okay, can you say something? It's not working. They can hear. Okay, let me check in with the audio guys. Yes, oh, wait, I have my sound low. Okay, can you try that? Yeah? Yeah. It's coming out of my speakers. Let me see if I can try it to go through the HDMI. Okay, what about now? Okay. It's not working. Let me check in with the other guys and please. Audio is not quite that good. Yeah, let me check in with them. Yeah, since I went to get someone to try to get it fixed. It's, alright. Yeah, we still have 30 minutes, so. Can people on YouTube see my screen? No. Okay. Okay. Yeah, I set the audio. I can hear you. I set the audio output to the HDMI port. So it should.
Sometimes it get messy, so maybe if you check again the system settings and audio and see what device you use. Also, you can check here.
Oh yeah, and yeah, but I tried to play a song on Spotify as well, and we did not play it through the HDMI. Sorry.
So look, please, so if you go on Google Meet,
Yeah.
and settings audio.
Yes.
What is here?
Here I have speakers. I can set it to HDMI, but see, I set it to HDMI now, and it's not working. I can hear you, and I guess it's disabled. I don't know.
So fine. I think it's going to be a lot of answering.
Can you speak again now? Maybe with the microphone. Yeah, it works actually.
Yeah, it works. Okay.
We can use the microphone. Yeah, it's okay. I mean, just in case some. Yeah.
It's just in case there's time for a Q&A session.
Yeah.
You can go like this, like moving
Well, will you want to be visible? Do you want to be in the corner as well? Oh no, you are hearing me on YouTube.
Oh, there's an echo.
Okay, so let's wait to see if someone comes and helps us out. Otherwise, we will use the microphone. Okay.
Yeah.
Okay, closing the mic now. Yeah.
Delay because
There is. Yeah, of course.
Oh, okay. Actually, do I hear you?
Yes, you should be able to hear me.
I wasn't sure if I heard you through you.
Yeah, I have the microphone. Yeah, you are hearing me through my computer.
Okay. Yeah, and I'm also, well, I'm going to see where I can hear you when you talk. Either on YouTube or...
No, I will share my screen with you as well. So let me. I can share my entire screen so that you can follow the presentation while I. Yeah, like this.
Okay, that would
Does this work? Yeah.
No.
Oh yeah.
Okay, instant notes.
Maybe hide the comments or...
Yeah, yes, I will go into slideshow mode. I don't know how to hide the comments now.
They're not going to show, I think.
No, they don't show on the slideshow. Like if I go here with this comment, yeah.
Do you need the speaker notes?
No, I added the speaker notes to the slides. So that is good. So yeah, I divided this one into two to make it easier
Okay.
for me to go.
Yeah, so I think 30 minutes is good. People speak faster when they stress, so
Yeah.
make sure not to speak fast, because otherwise it's going to be probably 15 minutes or something.
Yes, I will try to slow down.
Yeah, and I guess take your time. It could be too not stress.
Okay, so now I'm going to give Chincha my camera so that she takes some cool pictures of me.
All right.
So see you in 10 minutes. Okay.
Yeah.
Okay.
All right. Bye-bye. See you.
Yes. Yeah, so people online. There's one thing though, I will connect this Edelman on Google Meet because he was supposed to present this, but he did not come. I have him on a video call right here. But is there any way to get the audio to pipe through so that when he speaks, and this is for the QA only, so if there's any question, I might relay it to him. Yeah.
So I would like the.
This is like your other person that was going to present,
Yeah,
and he can't be here, and you
yeah.
have him on
Yeah.
Magic Genie.
Yes, I know I
We
haven't.
need sound out of here,
Yeah.
which I think is connected with
But
those
I
guys.
tried, but it's
Well,
not.
he just doesn't have the pod open.
Okay.
So we have to check with Gareth when he gets back.
Okay. Okay.
And I can go get it from the smoker. Sorry.
All right. So yeah, just that.
So you'll do the first one after when people come in. But you're up first.
Yes, I'm
Yeah,
the first
okay,
one and
good.
the.
What's your name?
Pedro. I don't have my badge here.
Yeah. Yeah. Tom. Nice to meet you. Okay, great. Thanks for joining us. Thank you for having us.
I'm just trying to pick up the hours. Okay. You can take one of the like they can create it, like use the Zoom and stuff. One like this. You can also. This is on the photos also.
Yeah, how do you change this? Oh, it is, okay. And I see this on the yeah, it's
And then you just have to click from right. Oh shit. Wait, let me. I'm presenting first, yeah. I'm Peter. Nice to meet you. Let me get my badge so that people can see.
Are you guys all set? I'm just going to check the connection on your computer to make sure everything is all good really quickly.
Also, I wanted to pipe out the audio from the laptop.
So we don't have a feed going directly in here. Probably the only way that they'll be able to do it is through the microphone on your laptop. But so then he can hear this in the room through the.
We'll have someone connected on the Google Meet, and he might have to answer some questions maybe. So when he talks, I would like to have like the audio feed. you know, the audio output, like when I select.
Yeah, that's what I'm explaining
Yeah,
to you.
yeah,
We're
it's
not
not
set
possible.
up for that right
Okay.
now or anything. So
if I
you
select,
have to be able. Yeah, you want to select Crestron. Is he on right now?
Yeah, he's on, but it's not working.
Does he
can
want to
try
try?
We can try with displaying the sound.
There he is.
Oh, yeah.
Yep.
Oh, now it works. It wasn't
Yep.
working before.
Yeah, I had to set it in your computer and
Ah, but
everything like
I
that.
said it. I think that some.
Oh yeah, you have to select the
Okay, cool.
Crestron on the sound and everything like that. It sometimes doesn't.
Yeah, okay.
Yep.
Cool. So, Adrian, you are on.
All right, cool.
Are you
Okay,
able to
so-
hear us all right?
Yeah, he can.
Yeah,
Okay.
yeah, sounds
Okay. Good.
pretty well.
So yeah, that will
Thank
be
you.
the microphone for the podium, and then also for questions, we have one over here. So you can just pull it right off the stand, run around with this. Sorry. And then yeah, you can just bring it to whoever you want. You're not using it or anything like that, so. Yeah, no problem. Yeah, I just wanted to make sure that yeah, no problem. Anything else, by the way.
I think I usually don't get bored of it, so that's why I like it. And I've tried Demon too a little bit, like that. But I'll try again now that I know you all. Yeah, I tried it actually. Yeah. Right when it came out, I followed you all on Twitter. I don't know if it's you specifically, but like I see some stuff on Twitter. And I'm like, So you're the main who's presenting?
I'm the one who's presenting.
Okay, so I'm not gonna, I don't really want to use too much, so like, you got control a half an hour, or like,
My presentation should last around 20 minutes.
Okay, perfect.
When I last time. So
Okay, perfect. Okay, so I mean, I'll give you some warning, but I'll stand up and you should, yeah, just let you know. Okay. You don't have to stress too much about it. All right, awesome.
yeah, I think I tend to speak faster when I present. So
Yeah,
it
sure.
should be nice.
You're gonna do great. Yeah. I'm pumped to hear it. Yes.
Well, I'm speaking right now.
I'm
handling the camera for the webinar.
Okay, all right.
So we would like you to just introduce from the podium.
Okay.
And you'll put that microphone.
Okay.
Thanks.
Got it. No problem. That was a good joke. I love it.
Yeah, let me check that everything is okay. Do not disturb. Yeah.
Okay, good morning, everyone. How's it going? Good morning. So we have a nice hour and a half track here, yeah, really looking forward to it. 3 nice talks. I haven't met the other 2 speakers. Are they here? Okay, all right. So hopefully they'll show up. One other reminder that I've been told to discuss with you is that there's a picture at 12:30 today, right before lunch, or right before lunch at 12:30 near the food trucks. So it's going to be like 600 people trying to get together, and I encourage you not to miss it. All right. Well, I think this presentation doesn't need any introduction. We've all heard about Genie, and we're all pumped to hear about Genie 6. And Pere, I cannot pronounce his name. I cannot roll my R's, but like Pere, who's a very nice gentleman, is going to give the first presentation. So thank you, Pere. Yeah.
Okay. Hi everyone, I'm Pere Jimenez, Data Science and Developer Advocate at Genie. And today I will be giving this talk about Genie 6 in place of the creator of the Genie framework, Adrian Salciano, who will be on call in case we need to answer any technical questions afterwards. Say hi, Adrian.
Hi, everybody. Hi.
And well, so yeah, let's get started with the presentation. Maybe I can take this. All right, so let me start with a quick overview of the status of the Genie framework today. Now, Genie framework is a full stack web framework that is formed by several packages implementing various aspects of the full stack, the main one of which is the Genie.jl, and it's the most famous one, implementing the server backend. Besides this one, we also have a low-code UI layer implemented by Steeple for building reactive user interfaces, the Searchlight package, which implements database connections as an ORM layer, and also first-party plugins that provide features like auto-reloading, authentication, etc. And on top of this, we also have in our product offering no-code tooling for improved not performance, but productivity when it comes to building web applications, such as the Genie Builder that I showed in a few days ago in our workshop, and Genie Cloud, which is currently in closed beta. So after this short introduction, This is the outline I will follow. This presentation will be focused on introducing the improvements that Genie 6 brings. So I will go over the most important of them in a little more detail. So Genie 6 at a quick glance. In our work to upgrade from Genie 5 to 6, we have attempted and we have had as our objective to make Genie a simpler, faster, and more productive Julia web framework. And so for this, we have enhanced the API, we have optimized a lot of code for performance, and we have added extra features to boost productivity. And so as a result, for Genie 6, we can say that we have a framework that is on par with other popular offerings like Django or Rails. And we can also say that it's very fast, up to 10 times faster than these other frameworks. And of course, all of these improvements propagate through the whole full stack, affecting things like template engines, routing, caching, etc., and all of the features offered by the Genie framework. So in order to go into a little more depth with the speed improvements, let me say first that Genie 6 is fast. According to some benchmarks taken with WRT and other tools, we can say that it consistently beats over 14,000 requests per second. Now, if we compare this to other frameworks like Django, Rails, or Sails, we can see that well, Genie is much faster, as at most they can handle these other frameworks 6,000 requests per second according to some publicly available benchmarks, which is less than half of what the Genie framework can do. So moreover, we can say that the Genie framework is stable. It has over 500 unit tests for the code stability. We also have a large user base and a native community of both users and developers built around it. And so Genie framework is mature, feature-rich, and it definitely is a production-ready web framework. One of the, now getting on to the new features introduced in this new version, one of the most exciting ones that has been very often requested by the community is support for running Genie on multiple processors. Now in this new version, Genie is using green threads to handle requests in parallel in a non-blocking manner. And we have also added experimental support for multi-process execution. And this can be used very easily with the typical Julia API, where we add some workers to our application, load the Genie package into each one of them, then we can declare routes into each one. We can declare routes into each one of the workers, and after we spin up the server, all of the requests the server is receiving will be served across all of the workers. Now we have to say that well, we haven't seen big improvements in terms of requests served per second. So in that regard, don't expect big improvements. What we have seen is decreased latency when answering to a request. But the most important part about this is that now a Genie application can be run in a distributed manner across computing clusters. And another request that is very popular among Genie users, especially in enterprise applications, is authentication. We have also improved the authentication plugin, since we have made some improvements to the Genie session.jl package by adding to it other storage options that increase the performance, such as Redis storage backends. Now, since Genie authentication uses this Genie session package, it's also benefiting from these storage performance improvements. And in addition, we have also added support for 2 new authentication schemes, namely better authorization for token-based authorization, which is used in APIs, and also for basic authorization, which can be used in various HTTP agents. Now, in our aim to improve Genie for this new version, we have deeply refactored some parts of the code, and the most important of this is the request parameters object, which I will explain over the few next slides. Now, the workflow with web application is as follows. the user submits a request to the server, or the web application. There, the web application unpacks the request and returns a response matching the received request. Yeah. Now, the challenge in this, well, for the developer is being able to handle a multitude of requests easily and at scale. In order to make the developer's life easier, full web stack frameworks provide APIs for handling requests in a safe and performant manner. Now, a key part of these APIs is the parameters object, which we can see depicted here in this figure, which stores all the relevant information about the request, such as the query parameters, files that have been uploaded, authentication, data from plugins, etc. And this parameters object is used throughout the whole web stack. Taking a look at the states of the params object in Genie 5, we can say that as of now, well, in Genie 5, the request parameters use the task local storage provided by Julia itself. So because of this params object was readily available at the global module scope, which could introduce, and this design was inspired by Rails, and it's not very Julian, since the direction Julia has taken is that it relies less on global variables, and it proposes more of a functional style. And this design can introduce some scoping issues, and also the parameters call in Genie 5 is not thread safe. As we can see here in this code snippet, where since the params is in global scope, we can easily overwrite it inside the route call with a simple variable declaration. And when we are going to trying to get some parameters from the request, we are not able to, since it has been overwritten. Then, with regards to thread safety, if we try to make a request for the parameters in the header in an asynchronous call, this would not work and would return a task fail exception, which is, well, quite a big problem. And so in Genie 6, we have revamped the request object. Now, each request will get its own isolated context.params object, and this object will expose all the relevant request data, such as the query, the payloads, the files, routing information, etc. This params object will be used to transfer information around the Genie app, between modules, plugins, and many other integrations. And moreover, this object is extendable so that any new plugin can incorporate its information into this request object in order to implement its functionalities. Now, if we look at the params object in Genie 6, we can say that we have solved the scoping and thread safety issues by right now, the params object must be explicitly passed to the route, okay, in order to be used inside of it. And besides, we have solved the thread safety issues, and now we can easily use a call to the params object within an asynchronous execution, and it will work. Now, the params argument is still optional, so if in your code you have route declarations that are not accessing parameters, they will still work, as depending on the number of arguments passed to the route function, Genie will choose which one to execute. Now, another feature that has been very often requested by developers is the ability to pass custom headers to the template engine in Genie that generates the HTML and JSON responses. With Genie 6, we can easily do this by modifying the fields in the params object. Here, in this example, we see how we instantiate params object, and we can easily access some of its fields, like the response headers, also the response status, and modify them. And once we are finished with the modifications, we can call the HTML generator and just pass to it the params structure, and it will be injected in the response at the header. So this brings us with a much easier way to include custom headers into our responses. Moreover, with this new parameters object, we bring a standardized way to pass information between plugins and modules and so on. So, yeah. And then, of course, this makes it easier for developers to contribute with new features, as we have a new standard way to implement this information passing. For instance, if we take a look at the authentication plugin, now it is easier to consume authentication information parameters through the use of the authentication structure by accessing its fields within the plugin itself. Moreover, now finishing with the parameters and moving on to workflow improvements that we have introduced in this new version of Genie, we have improved the workflow so that now there is automatic dependency loading, so that modules such as requests and responses are automatically loaded when we import the Genie package with using Genie. This is also the same for the context and the router modules. And this automatic loading of these modules makes it easier to develop, since you don't have to pay attention or worry about importing explicit dependencies. Now you can just use the function calls in these modules directly without having to add any more explicit dependencies. Now, moreover, we have also introduced a new Go macro that replaces and improves upon the Genie.load app call in order to load the Genie app before launching it. In line with these workflow improvements, we have also added the ability to eagerly load the environment variables upon using Genie. And this works for the environment variables defined in .env files in the same folder as well. Now, in Genie 6, if we look at these code snippets, we see that if we were to define some environment variables to say, let's say, the port that the app should use, when we start up the server, these environment variables would not be applied. That is, we would need to set these environment variables manually within the Julia code with the Genie calls. And now with the Genie 6, when we set up some environment variables, then, let's say, for instance, again, with setting the port number, when we spin up the server, it will automatically apply all of these variables. And as I said, this works for environment variables as well. In our line of improvements, we have added a new family of macros to the router in order to make it easier to handle the different types of routes that Genie can work with, such as get, post, put, etc. Now, as I said, this makes it easier to work with the router. And moreover, this new family of macros can potentially improve the performance of the Genie application, since what they do is they automatically wrap the router declaration in a function. And therefore, this can improve performance. Here, we have an example snippet of using this new post macro in conjunction with the new params object to define a new route. And for more router improvements, we have added a new small API for grouping together routes that share common paths. Let's say we have a long list of routes with a common prefix. Now it's easier to define them by using the new routes group object. With this object, it takes, we can declare it by passing to it a list of routes, defining each one of them individually, and at the end, we just add a prefix that we want all of these routes to have. All of them will be grouped together in an object, and then we can register all of them at once by calling the routes function. In the same line, we have also introduced a new group function, which will take as an argument a list of routes with a specific prefix, and then this will automatically declare all of these routes with a given prefix. And well, this is it for the improvements that we wanted to highlight for this presentation. There are many more, but time is limited. And so we can say that there are other improvements, as I said, not presented today, that have been made to the caching for improved performance. Also, I would have liked to give more details about the new sessions implementation, and also a lot of internal code optimizations and improvements in order to make the framework both easier to use, more stable, and faster, as we have seen. Now, there are a couple of plugins that still need porting, most notably those having to do with reactive user interfaces implemented in the Steeple package, and we are working on porting them over to Genie 6. And also, there's some other exciting features that we are working on at the moment, such as social authentication and static site generation. We're also going to do a big push to improve the Genie 6 documentation in order to make it easier for developers to get started with the framework. And well, as of now, the Genie 6 package is in beta. You can install it from the Julia REPL by adding the V6 branch of Genie. And we expect to keep the development of this beta for the next few months and release the final version in this September of this year. And well, this is it for this presentation for today. If you decide to give Genie 6 a try and have some feedback or some issues that you would like to have help with, or anything, discuss anything related to Genie, please get in touch with us. You can visit our website, open an issue on GitHub, or join our Discord community. And if you work at a company where you are working with a Genie application, and you think that you might benefit with some expert help in bringing your development speed even faster, please get in touch with us, and we will be glad to discuss our consulting services. And well, this is it. Thank you very much for attending. Now we are open to any questions that you might have.
Great job, Pere and team. Yeah, there's a few questions, and we have plenty of time. So let's. I don't have my glasses on, but I can see there's a gentleman in a red. Yeah.
Wait,
I'm
there's a microphone.
Oh, there. Oh, here. I think go up there. Bring it up. It'll work now.
All right. Thank you very much. I'm very excited by all these new features. I just wanted to ask you thought about new authentication plugins. Will one of those implement JSON Web Tokens authentications?
Can you repeat again?
The JSON Web Tokens authentication.
Okay. Let me relay this to Adrian because he's the one. Did you get that, Adrian?
Yeah. So about JSON token authentication. So at this point, we already support for generic tokens, which are generated automatically by Genie authentication. But we haven't looked yet into establishing a certain format like the JSON authentication tokens. But definitely we can take a look at that because now we have all the functionality to support different types of tokens. So yeah, actually it would be a good idea to edit for the release in September.
Okay, thank you very much.
Thank you.
So I have a question about, I've wondered about the relationship between Steeple and Genie. Can you explain that a little bit?
Do you want to explain it, Adrian?
Yeah, sure. So Steeple is a Julia library or an ecosystem of Julia packages. that provide reactive user interfaces. So think of something like Dash maybe, and Steeple practically runs on top of Genie. So Genie provides the low-level infrastructure to set up a web server, to handle connections, to basically manage all the low-level features of communicating over the web, while Steeple comes on top of it and enhances what Genie offers by, for instance, real-time WebSocket connectivity, and there's Steeple UI, which is a Julia package that provides UI components so that you can quickly create a user interface for data dashboards or data applications. It includes form elements, so like sliders and drop-downs and inputs and tables and tabs and everything that you need to create a data dashboard or a data app. It also includes, for example, Steeple Plotly, which is a plotting package that also works together with Steeple UI and Genie, so you can easily render plots in the app. So basically, it's a reactive application and UI library that runs on top of Genie.
Okay. Thank you very much, Adrian.
Thank you.
Any other question? Oh, there's one question. I'll head up the stairs here.
First off, I'd like to thank you for Genie and all the time you spend on Discord. I know you've helped me out with a few questions that I've had there, so that's really, really awesome. Thanks. My question is a little bit related to that in that Genie, when it works, everything is like magic, and it's just like, wow, this is really awesome. But at least when I develop with it, or just code in general, things don't always work. And when things don't work, it's such a intricate interaction of many different layers. There's the web browser, JavaScript, there's CSS, there's the Julia side at the server and all that stuff. Do you have any sort of tips or tricks you could suggest for debugging when things go sideways?
Microphone doesn't work? Okay, now. Yeah, I agree that being a full stack web framework, there's many moving pieces that are glued together, so it's sometimes hard to debug them. My first suggestion will be to ask for help. Join our Discord, and we reply pretty fast. In a few hours, you will have some help. And we are also currently working on adding to the documentation guides on how to solve common problems, like to debug issues, and where to go, like, for instance, when you have an issue with the reactive user interface, how to inspect, let's say, in the Chrome developer console, where to look for in order to be able to say, okay, this is what might be happening. So what I would say is please tell us the kind of issues that you are having, and every time we come across a new issue, we make an effort to add a new guide or a new example, helping future users who might come into the same issue overcome it. So yeah, it's I know it's hard to develop sometimes, but it's ask for help, and we will glad to update our documentations. And next time, just search for it in the docs.
Thanks. It's not just me.
Yeah, I know.
Any other questions? Any other questions? Okay, well, thanks again to Pere and the Genie team.
Thank you. Thank you. Okay, see you, Edelman.
Here.
Oh, right here. Hey, how's it going, Carlos? What's up? Good. How are you?
Can I charge your mine?
Oh, yeah. Yeah, sure.
have some audio, but if it doesn't work, it's fine.
I need to set it up. Can you go to like the sound settings? Just select.
Great job.
Settings. Should be a Crestron option.
Maybe you can try a slide that has sound and check if it works.
Yeah. Normally it will say like Crestron or something.
Oh, oh. Well, one of these slides has a sound. This. No, it's not working.
Oh, okay. Go back to your sound settings really quickly. Got a turn. Okay, try.
Yeah. Okay, let's try that one.
Yeah,
Maybe that one works. No, that's this. Well, I can put it in the speakers. Oof.
Yeah, shit. Yeah, that's super weird. Oh, I'm so sorry.
That should be fine.
Okay.
Okay. Okay.
Oh, yeah, we have those. Yeah. Yeah. Amazing. Yeah, and also Valkyries. So you went to the binaries? Not really. No. Somehow we missed the weirdism friends. I had some friends. We went to Paulo Merenda's house. I still remember. Is that the one that has like names? Yeah. Oh, yeah. Amazing. Amazing. So, yeah, my wife and I want to go back to Central this week. All right, it's 11 o'clock, so yeah, that's fine. I'll introduce you for a second.
Okay, we have our next speaker here, Carlos from Santiago, Chile. Also King's College, right? He's going to be filling us in on his, is this a new package, relatively new? Yeah, new package about MRI simulations. Take it away, Carlos.
Okay, thanks for the introduction. Well, I'll start asking, how many people here know what MRI is? Like, raise your hand. Okay, some of you know. How many of you have been inside an MRI? Okay, more than I expected. And how many of you know actually what's happening? Maybe not. Yeah, okay, some. Okay, so I know my public here is not MRI experts, right? So I will not be going straight to the code. I will explain what MRI is. Okay. I will explain briefly what MRI is and why should you care about MRI, why MRI simulations are useful, and then how I've used Julia to basically create an MRI simulator that satisfies all my needs. And probably that part is the part that will be more important for you. But let's start slow. So first, the introduction about MRI, then why it's useful, then COMA, or my simulator, and how I approach this with Julia, and a little bit about the open source MRI ecosystem. Okay, so what what is MRI? MRI, or magnetic resonance imaging, is a type of medical image, or that is particularly tomographic, so you can see the body from the inside. And by varying magnetic fields, that's why it's called magnetic resonance imaging, you can change some properties of the tissue and measure inside the body. And you can even have like amazing images like this, having a volume of the heart or the brain, and measure various properties. MRI started with two guys here. First, Paul Lauterbur. That doesn't matter what he did exactly, but he was one of the pioneers in MRI. He called it pseudochromatography, based on a Greek word. It's good that that name didn't catch up. And also Peter Mansfield. That was one person that added like an additional thing that made this MRI actually useful. And these two won the Nobel Prize, and even Peter Mansfield was knighted, and now is Sir Peter Mansfield. So you can see that this is an important topic. But how does it work? Well, most of you know how a concert works, right? You have multiple instruments, and you have different partitures for each one, and you play them all at once. Well, MRI is kind of similar. In the concert, you have this sequence of notes, and you have the instruments here, and you have the sound, like this beautiful sound that is not working. Okay, I will not put a lot of it because it's going to YouTube. And so yeah, you can imagine you can create beautiful songs with this partiture or sequence of notes. MRI is kind of similar, but instead of an instrument, you have this scanner that has a lot of components inside, and you control them all independently to produce an image. But instead of like notes, what you have are signals that control each of these components. So it looks more like this, and the sound is not as good. It sounds more like this. So, not as good as a song. Okay, so for the MRI simulation or virtual MRI experiment, basically you need a few ingredients. One is the phantom or virtual object that has some physical properties defined in each point of space. And you have the sequence, that's basically how you control these magnetic fields to produce the image. You put all of that in the scanner, and it produces an image. But that's what people think. It's actually not like that. That scanner thing is actually doing some crazy stuff. You are not measuring the image directly. What you're measuring is the magnetization of the spins that are processing due to the magnetic field. So it's quite complicated. But the main point here is not the equation or that you're measuring the magnetization. The main point is that you're having indirect measures of the object. So you have a function here or operator called encoding operator that represents everything that is happening in the MRI. You have the image or the properties, and you have the data that you're measuring. And the important thing here is that all of the tissues have different magnetic properties here in yellow, and you can change the sequence in blue there and produce different types of images that have different information. And this is the part that is very useful clinically. Okay, so what's MRI simulation? Basically, the MRI simulation is how you do this forward problem, or here represented by the encoding operator, in an efficient manner. And instead of the image, you actually get this, the raw data or K-space. For those who know about the Fourier transforms, this is kind of similar to the Fourier transform of the object. And the inverse problems, or the reconstruction, or how you get the image, is like this. So you have an optimization problem with a simplified encoding operator that is now linear, so you can have like derivatives and stuff like that, and a regularization term or prior knowledge. And you don't have the full Fourier transform space. You have a soft-sampled space because you want to make it fast, and we all know that it's very slow. Okay, so you're basically going from this to the image or object. And basically, there's two approaches on what you want to reconstruct or get from the MRI. One of them is the weighted image that has all of these magnetic properties like in a soup, like you cannot differentiate between them. They're all together. And on the other hand, you have this bento box that's very well organized, and you have each property in their own component. And there's these two approaches, and you can have one or the other. Now is starting to be more popular, the second approach of having everything with the units and physical meaning, and not so much with a weighted approach. And here I put it as a fun thing that is in the manual of one of these scanners, that the MRI is not a measuring system. So basically what we're doing is not something the MRI was developed for. It was developed for this weighted imaging, not for measuring the properties. So you need to do some stuff to disentangle all of these properties. Okay, so amazing. How do we measure this weighted image or this map? Well, you go to a paper. Okay, this method gives me this result. Okay, how did they do it? Okay, they use a different scanner from mine. I have a different brand. And in the paper, the definition of this sequence is not as good. And not only that, but some parts are proprietary, and you cannot even see them. So this is where I wanted to create a simulator. This project started in the pandemic, where I didn't even have access to a scanner, because all of this COVID thing, obviously. I couldn't even access the scanner to scan a healthy volunteer. So I had to do stuff computationally. And another thing is that each scanning hour is pretty costly. So you cannot do a lot of experiments in one person for 10 hours. One, he's going to, or she's going to get tired, and also it has like a monetary implication. Okay, so I'm not the first one doing MRI simulators. There's plenty, but for mine, I try to target some specific aspects that I think Julia is particularly good at. One is that this proprietary closed version of the sequence was not the approach I wanted to take. I wanted to use open definitions of the sequence that are available. People can program these open definitions of the sequence, post them in their papers, and also test them in the scanner directly. And I wanted to, instead of using the scanner, use my simulator and try a lot of things and then put it in the scanner. So you can kind of optimize your sequences. The other thing is that not all the MRI simulators have the eye, or the imaging part. So imagine you take a photo and you look at the result and you see this. So it's not ideal, right? So an MRI simulator needs to include a reconstruction part to get this data and put it as an image. And the other thing is that some simulators are not directly simulating these block equations. They are just simplifying linearizing operators, and that is obviously good to make the reconstruction fast, but it's not good to model the system. Another thing that is in the story that is way too common, I think, is that when you try to install a simulator, this simulator looks very nice, the paper has great results, but it doesn't work. The CUDA version was different, they were compiled with this version, the library was something that you cannot install in Ubuntu 22.04 because it's deprecated. So many problems that makes reproducing results very difficult. And the other thing is that when people do their PhD and they develop MRI simulators, they kind of use MATLAB as an interface to C++. And that PhD student or that person needs to be an expert in MRI simulation that, as you already saw, is quite complicated, and also an expert in C++ to make the code fast. So then the next poor PhD student comes and spends 1 year trying to understand what the other guy did, so it's a little bit inefficient. And also because some types of people need different things. So for example, students don't care about the efficiency, the extendability, and stuff like that. They just want to play with it. So for that, an easy-to-use graphical user interface was very important. And also, they prefer to do stuff without programming at all. On the other hand, researchers really care about novel things. They want to extend this simulator for their research. If you're not able to do it that easily, they will rewrite their simulator, and that's why there's like 400 of them. And also, it's impossible to extend a simulator if it's not open. How can you add stuff if you don't know what's there? Also, it needs to be easy to reproduce the results. So if you publish something, this is the environment, how I run the code, blah, 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 and you can reproduce the results. That has a huge importance in science. And obviously, they want stuff that they will not get by writing their own simulator. So for example, that is being optimized, so it's fast, that it has very accurate and tested results, etc. So that's something that is not easy to do from scratch. So it needs to add some benefit for them to consider to use this simulator. Okay, so those are the things I wanted to target for my simulator. Oh, also I forgot cross-platform. It's super important that people, especially students, can install this in their computers. And here at the right, there's just a brief landscape of the MRI simulation world. And as you can see, most of them do not satisfy all the requirements, and, well, actually none, at least the requirements I set up, because they were developed for different purposes. And now I'm targeting something more general. So remember this: open source, cross-platform, graphical user interface, fast and accurate, and extensible. So how do I do this? Well, in this conference, I probably don't need to convince you that Julia is a good programming language for this, right? But in the MRI community, I need to explain. But yeah, basically, Julia has great GPU support. It's very easy to do multi-threading. Graphical user interface is quite easy to do as well. So this is what, and also it's obviously fast, and it has a reproducibility aspect very well developed with the manifest.toml files, etc. So I developed this simulator to accept a few files that are the definition of the sequence, the phantom or virtual object, and this comma simulation block basically generates the data that is also an open standard developed by the MRI community. And you can use already available MRI reconstruction packages, here MRI Rico, and that is written in Julia, of course, and can take this raw data and generate an image. And this is all contained in a graphical user interface for people like students to try it and just click buttons and play. Okay, this is, has a lot of information, but I'll try to go by parts. So the first thing, you cannot see, wait, laser here. So the first thing I want to mention is the phantom or virtual object. So you have one magnetic property for each point in space, basically. And the cool thing about this problem specifically is that the magnetization of the or whatever is going to measure the MRI machine is independent from one another. So you can parallelize them. Basically, one pixel is one partial differential equation, and you can solve them all simultaneously. So this problem is made for parallelization. So the first thing I did is to separate this object into multiple chunks with the views macro, basically, to not add more memory. And all of these chunks are passed to different simulation blocks. What's interesting about the MRI problem is that it has been very well studied. And depending on the sequence, different sections of the sequence do not need to solve the full block equation. You can solve just one simplified version of it. So if you are able to identify beforehand which parts are easier to solve, you don't need to do the full block simulation. So that's what I did. I tried to tag each section of the sequence after discretizing them, because we already know the sequence. We don't need to do like adaptive time stepping and stuff like that. We already know what's the most efficient way to sample this because we know the sequence. It's not something that will be a surprise. So we can pre-compute the time points. We can pre-compute which block of the sequence is calculated in each type of simulation. So here, one is called excitation, one precession. And we also know in which blocks you actually need to write something. So here in MRI, it's called analog to digital converter. But it's basically when you are starting to listen what the signal is, you're not listening all the time, just in certain parts of the sequence. And when you're listening, you basically save that to a matrix And this is done with multiple threads, and each thread writes to a different matrix that then you can add together. The cool thing about this is that using abstract arrays, you can use this in the CPU, but if you initialize everything as CUDA arrays, you're doing everything in the GPU without changing the code at all. And another thing that is very important was the extensibility part. So all of these blocks, or simulation blocks, or simulation types, are specialized but for a simulation method, an abstract type. So they have as an input an abstract type, that the default one is block for the block equations, but you can change it to whatever you want, import all of these, redefine them as you want, but you have the graphical user interface, you have all of the reading and writing of the functions and the reconstruction, so you don't need to deal with a lot of stuff they already take care of. Okay, so this sounds nice, but obviously I was coming from MATLAB, and when I tried to program something, I don't have all the knowledge to do it efficiently. So the first time, actually, I did it quite inefficiently. In each block, I passed from the CPU to the GPU. So there's a memory transfer. Then the excitation block, I didn't do with the GPU at all. And I cannot overstate how useful the NBTX or NSide tools were for debugging this. In Julia, doing this is so simple. Like, you just put a profile macro and you tag with the NBTX range macro each block, and you can easily see which blocks are being done correctly in the GPU, where are the memory allocations, what parts you need to fix. Okay, so what did I did this? Because the simulator was not faster than the competition, so I wanted to be fast. So I basically rewrote the simulation core to do all of this efficiently, replace all the allocations with in-place operations, improve the type stability. Everything now is float 32. You don't need to take care about it. And also try to remove the need for memory transfers. I do a first memory transfer at the beginning of the simulation. You simulate everything in the GPU, and then you have the result. If I'm doing this, code that was already fast is now faster. Now it's 5 times faster just by taking care of this. So now how you can see that is actually better, because this blue part here represents the GPU usage. So the more blue is better. So if we go back just briefly, here you can see that this blue, there you have memory transfers, a space that is just waiting, doing nothing. So it was quite inefficient. And now it's very fast. But it could be faster. And by doing this, we compared our simulator with the competition, basically. Jambreeze, that is the most used MRI simulator, but it's only parallelizing this in the CPU. Takes about 7 minutes for one simulation. And MRI Lab, that is also written in C++ with CUDA, takes about 1.5 for the only CPU version. And for the GPU, we are actually faster than these especially written CUDA code. And I'm using CUDA arrays. I'm not writing a kernel at all. I don't know how to do that. But even by doing this with CUDA arrays, it's faster already. But it's not useful that it's fast if it's not accurate. I can produce garbage very fast, no? So we need to compare our simulator with another one. This Jambreeze simulator I didn't explain, but it solves the block equations like with the whole equation. It uses an ODE solver, so it's very accurate. And when we compare, the results are basically identical. You can see in the bottom of the screen the mean absolute difference in percentage. It is below 0.1 in all the cases. We compared this in multiple scenarios, and it was always accurate, but like even 300 times faster. The cool thing is that now that we simulated this with another simulator, you can add this as a test. So in the test, you simulate this, check if it's similar to the thing that it's supposed to be, and if it's not, it fails. So it has a meaning the test. It's not just calling functions and see if they work. To test that it was easy to use, we had a student experience with students that were learning about MRI. And this is the first version of the graphical user interface. It was slow, it was bad. It was developed with Blink to be easily extensible. So it's just HTML, CSS. I'm using Bootstrap for the styling. So I didn't have to do a lot of stuff. And even with this ugly and not so optimized code, it was already like 10 times faster than Genbreeze. That was the other simulator that everyone could install, Mac, Windows, and Linux. We took the feedback of all the students and improved the graphical user interface. So now it's not only faster, it's more beautiful. and the idea is that you have like this sequence part that you can just load a file, load a file, load a file. Simulate is just a button here, and reconstruct is also a button. And you can see the results here in the image tab. And obviously, MRI people use MATLAB, so we included the export to MATLAB option. So you have the results computed in Julia very efficiently, and then you can export them to MATLAB if you want. Comma was thought to be open, so everyone can extend it. Yesterday, I learned that this is considered a monorepo because it has multiple packages in the same GitHub. And we are using CI for all of them. And we are also testing all of them. And we have very good code coverage for all of the submodules. And most importantly, it's very easy to install. It's just add comma MRI, and it just works. It works like cross-platform. You don't need to like compile stuff in C with the correct version of CUDA. It just works. Another cool thing is that for the documentation, we use Literate and Documenter, so you can generate just one .jl file that has everything for the generation of the documentation. You can also export it as a Jupyter notebook, as a Julia script, and run them in your computer, and you should be able to reproduce the results. One thing we want to include is a binder here, so you don't need to have Julia installed at all, but that's the next step. For the test, I already kind of mentioned that, but you can simulate compared to the gold standard and check that the error is not more than 1% or 0.1%, and this is a very good test. And we did this for all the functions in each submodule. And in our experience, one test equals one bug. Like every time we added a test, we found a bug in, in Windows, in the Julia 1.6, or in Mac with Julia 1.8, in the GUI, or it's so useful to use tests. And this is obviously very obvious for you, but in the MRI space, people do not test their code, so it's just buggy. And to certify that this is cross-platform and it works everywhere, even the UI is being tested, and with the CI, we can test it in Julia 1, 1.8, 1.9, and we also can test it in Ubuntu, Windows, and Mac, and generate the documentation automatically from using Literate. Okay, I'm almost finishing. So I just wanted to briefly mention that the MRI community is taking notice of Julia, and a lot of people are having meetings. One of them, me, there in the corner. And we're porting some reconstruction and simulation code to Julia, and it's starting to form an MRI ecosystem. And yeah, it's being noticed and it's being used. And this has huge implications in the speed of reconstruction. And even if it sounds only a computational problem, it has a huge impact, because if you're trying to reconstruct an image and it takes 5 minutes and you cannot see the result, you cannot repeat that scan. You need to just go with it. But if you can see it in 30 seconds, you can reacquire or play with it a little bit more. So this has a lot of implications in the clinic as well. Yeah, I wanted to briefly acknowledge my colleagues at King's College London and also in Chile, and thank you everyone for listening.
Great job, Carlos. And happy to entertain a few questions here. We have time. All right, here. Let me. I'm going to bring the microphone. Oh, here. You hold this one.
Hey, so yeah, great talk. I used to work in MRI a little bit. So my question is, like, are people using these tools for sequence design and optimization? Because yeah, that seemed to me to be a really big thing that you'd like to do with Julia and MRI, I guess.
Yeah, exactly. So generally, the sequence optimization is not being done. So one of the things I did, for example, I'm not showing here, is that you can put these objects that are the sequence objects and optimize them using jump or stuff like that. And you can find like optimal, with a certain definition of optimal sequences using these simulations. And you can improve the image quality a lot. The other thing that the simulations are quite useful is that, for example, instead of the weighted image, that is the traditional way of looking at images, you want to reconstruct the properties like T1, T2, or the things I showed. You can simulate like all the combinations T1 and T2 and then just do a dictionary matching and check what the actual properties were. So this is useful, yes, for sequence optimization, but a lot for quantitative imaging as well, and reconstruction to have a more accurate model. I'm not sure if I answered your question.
Yeah, I think so. I guess one thing that I thought was really interesting about the whole space was it seemed to be wide open to have a joint optimization of the sequence design and the reconstruction. And I was hoping that people would start doing that when I used to work in it.
Oh, can you repeat the question? I didn't hear it very well.
So like a joint optimization of reconstruction and sequence design.
Yeah.
And I thought that was like one of the most interesting things people could be doing. Not that the position I had let me do that, but I was hoping that you would say, yes, people have started to use these tools you're building to do that.
Oh, I'm not sure if I got it correctly, but people are doing joint optimization of the sequence and the reconstruction as well.
Exactly, yeah, joint optimization. Because
Exactly.
like reconstruction and the sequence like go together hand in hand.
Exactly, they're putting both together and they're optimizing the reconstruction with the sequence or the other way around. Yes, people are starting to do that.
That's amazing. If your work enables that, that'll be amazing. Yes,
Well,
very nice. Thank you.
Hopefully you can do that with Enzyme. I haven't tested it yet, but
Yeah, that would be cool. All right. Well, thanks a lot, Carlos.
Sorry?
Do you have any audio?
No, no audio. All right. Test. Yeah, it's okay. Yeah, we can just.
You guys can just go.
Yeah.
Here, I don't know you guys, but it's who's Cedric? Which one's that? Oh, you're Stefan. Yeah, it says Cedric. Okay. So what? Where are you all from?
I'm from France. I'm from France.
Okay, where are you from?
The UK.
Okay, nice. All right. Well, yeah, let's get going. This is awesome. A topic, production app for Julia, right? Sweet.
Let's hope you enjoyed. All right, let's get going. So, hi everyone. My name is Cedric.
I'll be presenting today with Stefan, and we'll talk about essentially how we've been using Julia at Planting Space, and also how we deploy the production app with Julia. So first, a few words of context. So at Planting Space, we are developing an explainable answer engine, and the idea is that we have some kind of web service where we can answer any kind of requests or incoming queries and provide a statistical distribution as output. So essentially, we don't provide a single answer, but a set of answers ranked by probability. And the way we go about that is we take the query, and we have a system which will know about lots of different pieces of knowledge, and then synthesize an actual Julia function, given the query and the different bits of knowledge, the primitives that we have. And then run this Julia function with probabilistic programming to then have the statistical output. We do this so that we can have also a fully transparent reasoning, so you don't just return the answer or the answers, but you also return the procedure, including all the steps that were needed in order to derive this answer. So to build this, we're between about 35 people. We're all fully remote, scattered across different continents. We are still in the initial development phase, meaning we don't have like a product to be sold yet. We're still working more in a researchy development kind of phase. We're about 20 to 25 core developers developing this. And something to note is that, which is quite cool, is that all of our backend uses Julia. The frontend uses, well, TypeScript and JavaScript, but we'll be interested in backend here. So first, it might not be so obvious why we chose to use Julia in the first place. So let's go over the main points. First, it's really a high-level language. It's great if you want to prototype. And given that we're developing something really quite innovative, we do need to have some room for iteration on it. And Julia helps a lot with that. There's also that it's fairly simple language to use, to learn, to read. It's very easy to go through a code base written in Julia. We really love that. There's also the performance aspect, of course. With Julia, we know we can get performance when we need it and achieve as much performance as we need. And also, it's very well suited for just numerical computing, which is, we do a lot of numerical computing on the types of logic that we design. One other thing also is that we do tend to generate code a lot because, well, we generate an actual function, so that means you need to build some function and then execute that, like an actual Julia module. And for that, we use a lot of the metaprogramming facilities. And furthermore, we also use a few domain-specific languages for a few internal parts, notably, to really help a lot with productivity. And it's really cool that we can do this. There are a few downsides, however. So it's not as easy as, if you want to deploy something really quickly, you can use Python. You have a plethora of tools available to you. So there we need to put a lot, well, not too much effort, but quite some effort into developing some components that might not be so ready to use in Julia. There's also that, given the type of product we're designing, we need a fairly low time to first answer, kind of time to first X for us. And well, we know that Julia isn't really made for very low latency applications, but there are ways to mitigate that, which work fairly well for us that we'll cover in this presentation. There's also one aspect, I guess, a more social aspect, is we don't have so many Julia developers out there to hire, and so when we need more hands, we essentially have to broaden our scope. And for that, we just try to find good programmers, and then rely on the fact that Julia is fairly easy to learn, with also a carefully designed onboarding to get so that people can get up to speed with Julia and contribute quite easily to initial tasks. Now we're a bunch of people, as I mentioned, 20, 25 people around that, developing Julia code. And so the way we go about that is a bit non-standard, but a few organizations have done similar things. So essentially, we have one monorepo, where we have all of the code mostly lives in one place, so it's easier to set up, to understand what is where is what. And then we also have one main package, so we don't have like multiple different internal packages. We just have mainly one. And there are a few reasons for this setup. The monorepo one is that it's just easier to, like if you want to make bigger changes, you don't need to scatter your pull requests across different repositories. You just have one. It's also easier to have just a continuous integration setup in one repo, not multiple ones. For the using only one package, one aspect is, as I mentioned, we have a very iterative development process, and sometimes even our core data structures need to be changed and iterated over. And it's just easier when you don't have to maintain interfaces between packages, like explicit interfaces. So things can kind of tend to move, and until they solidify, it's really nice to have some more flexibility in that regard. There are other approaches, of course, when you have a small to medium-sized team developing Julia code in an organization. You can have, for example, a monorepo approach, but with multiple packages. You can use a local registry or not. Depends if you want to use semantic versioning, notably, with compatibility bounds. You can otherwise use multiple repositories if you want to emulate some kind of open source ecosystem type of development, even though it might be proprietary code. So they have multiple repositories, maybe multiple developers working on different repositories each, and so on. So now, as we use this approach with a monorepo and one main package, we do need to make sense of the code. We have so much code that no single developer has a knowledge of everything that is in there. So we need to structure our code a bit. And for that, we rely on Julia modules, and notably on some modules for that main package, to design sorts of self-contained units of code where essentially have somewhat of an explicit interface between what a package imports, what it depends on, or a module, what a submodule depends on, and then what it can provide to other submodules with exports. And we are quite strict about this, so that then our code base is structured in a way that is really easy to understand. And it will be even easier also for us to analyze our code base and perform some form of code analysis that will be useful to develop a few tooling pieces. All right, so now I'll hand it over to Stefan, who will talk more about the tooling that we developed and also how we facilitated our workflows.
Yeah, hi, I'm Stefan. So as we just heard, our team is perhaps a little bit, so our repository is a little bit larger than the average, than the average Julia repository. And the other thing is, we heard yesterday at the package analyzer talk that the average Julia repos contributor had about 2 contributors. So we have a lot more people than that. Which meant that to work effectively, we had to build a few things here and there to make working together a little bit easier, and perhaps a bit sort of uncommon practices that I'm going to describe now. The first one, perhaps, is that we commit our manifest into our package. Normally, I think a lot of, like most packages use compat bounds, but that didn't quite work for us for a number of reasons. The first one is that we're building an application, not a library. It's only us that needs to use it. We don't need to be compatible with like a wide array of other combinations. What is important for us that for all developers, the environment is exactly the same, which also means that we want to avoid accidental breakages. Like even though compat bounds and semantic versioning has a very clear rules, sometimes maybe one developer has already loaded some patch version or like some patch update, and suddenly everything breaks, but not for the other developer who hasn't done it yet. So we commit the manifest to the repo, but we still want up-to-date stuff. So we just once a month roughly update all of our manifests, all of the dependencies in one go, run an extensive test to make sure that everything still works, and we just commit it in, and that is actually quite neat. There's some inconveniences involved in that. The first one is that we need to dev our main package by relative path in sort of sub-packages like docs or like a workbench/playground repository. And so that's a bit of a tedious process sometimes. Like we're really waiting for this like sub-projects idea to enter into PKG. That would be really, really nice for our workflow. The next thing is that with so many developers, we really want to reduce testing time. We have everyone, basically 25 people-ish, working on one repository. And we have a fairly high number of MRs, that with many small MRs going in. So we really want to reduce testing time to reduce developer latency. And to deal with that, we have 2 things. The first one is monorepo usually comes with a large number of tests. We don't want to run all the tests all the time because usually only a small percentage of the code base actually changed in a given MR. So we really ideally want to run only the tests that are necessary to run, and a few details on this in a minute. And the other thing is that because we only update our dependencies every so often, we'd really only want to pre-compile them or like compile them as little as possible, maybe only just once. So using a system image, and I know there was a talk yesterday that basically concluded, system image, maybe just don't. But actually we had some quite decent successes with it. So the first one is what we call change set-based testing. Cedric was explaining earlier our module structure, which means we have these small sub-modules, very clear rules on you can only use exported symbols, and there's a very clear correspondence between sub-modules and testing files, which means that in this specific scenario, we can actually then answer a question that is usually very difficult to answer, which is, if you make a change, what has been affected? So in our scenario, if, say, submodule 10, something changed, and then we know that submodules 2 and 5 import symbols from that submodule, then we only need to test 10, 2, and 5, and of course the overall integration tests, to basically cover, or like have a fairly high confidence that covered all the changes that we made. It's of course a fairly conservative estimate, but in our experience it actually works quite well and really cuts down on sort of average CI time for a developer. So that worked really well for us. The other one is on the system image. I mentioned before we have a fairly large number of dependencies, don't want to pre-compile multiple times, and we only rarely update them. So it really makes sense for us to build a single system image with all the dependencies. Some of this was grown before 1.9. We actually might change this a little bit now that there's the package images available. But in our sort of small example, it only takes us about like 11 minutes, plus maybe CI setup to build this image, and it saves us 3 minutes on every main CI run. That is not even to speak about CI on MR or merge requests, and that saves us 12 hours over the month. Doesn't sound like all that much, but also like it's a fairly small effort for actually an outsized reward compared to what we're doing. A few other small things here and there we do. The first one is what we call auto-formatter. It's quite common that there's format suggestions, even in open source repos. That was a little bit too inconvenient for us because you have to accept all of them anyway. So if it's not really a choice, why even present it as a choice? Why present it as a suggestion? So we just go straight ahead and have a bot auto-commit any distances between, like any issues, like any differences with formatting that might not be there already. So that's very convenient for us. The other thing is, I was mentioning change set-based testing earlier. Obviously, the immediate criticism could potentially be that there's a risk here that we didn't fully cover some impact that a change might have had. So we actually have a stopgap here, which is a result of GitLab. I think there's also a talk tomorrow about GitLab CI, not by us, but I'm very interested to hear about that as well. But so in this context, what we can do is in GitLab we can run on the theoretical change of main if the current MR was merged already. So if that succeeds, we know that once it's actually merged, main will still be intact. And there we just run the entire test suite, but then we only run it once for each MR. And the last one is stochastic testing. We don't want to fix the random seed, because that is not quite robust enough for us. It could be that somehow accidentally we have fixed the one random seed when it always works. And actually for, if we picked 5 other random seeds, it doesn't work for any of them. So we just don't fix the random seed. Every test run is different, which means sometimes it fails. And then we have built some logic around that to say, okay, how likely was this to happen? Like, was this a 1 in 1,000 event and we just run it again and then, then it passes and it's going to be fine? Or do we actually, did we actually break something in this test and now we need to diagnose a little bit more? Like that is, but still, there's still very much work in progress for us. Yeah, so this is in terms of tools and like sort of small bits and things here and there that we use to develop. So what does all of that lead to? Like, what are we trying to do with all of this effort? What are all of these tools? And that's the title of our talk, towards developing a production app. So what is our product and what are we doing with it? Oh, that was one too far. So the deployment overview that we have is that we have this system which is supposed to answer queries. which means we need to be really receptive to changes in demand. It might be that something has happened and suddenly a lot of users come in and have some question about something that happened, or I don't know, a variety of reasons we want to scale very quickly. And this is why Cedric is saying we want a low time to first answer. We want to be able to very quickly spin up a work, and it needs to be ready very quickly to answer a question. It doesn't quite work for us to say, okay, we spun it up. Now someone please sacrifice themselves to run the first query so we can get the pre-compilation out of the way. Like someone has to live the 1.5 minute or so that it takes to pre-compile. We'd really want to be quick about this. So to do that, there's some system image involved, which I'm going to talk about in a next slide. But the broad infrastructure for our product is that we have this Docker image, which we deploy in AWS Lambda, which contains the component, a first component to listen to potential requests. We've reverse engineered here a little bit the AWS interface, and it's basically just built on HTTP, waits for the next request to come in, and when one comes in, dispatches to our underlying Julia or like our underlying core product, computes the result, and then sends it all back. And yeah, so this system image, actually, we initially used to use Amazon Linux 2, but there's some issues with that, so we actually built our own custom Julia image based on the official Julia Docker image that you find on the Docker Hub if you go on the Docker Hub and search for Julia. So we just built on top of that and put in the right sort of components to mimic all the other things that more established languages like Python have in their Lambda-specific Docker image. Yeah, so what else do we do? We have obviously these components that are just needed to make AWS Lambda work. How to make it fast? I mentioned the system image already, so that is effectively the main secret sauce in a way. Again, there is the word of system image, maybe just don't, but the results are actually really good. Like if we just use our core application, and then I've normalized the plot on the right. With no system image, it actually takes quite a while. Then if we just add a system image without anything else, then actually we get like barely 5%, or like maybe actually it's less, like 3% of speed up. Still not really worth it. But then the secret sauce comes in with a trace file. So we actually have a fairly substantial trace file from our unit tests and some additional tests that we built. And if we include those into the building process, it takes a lot longer, but our first query is only like less than 10%. In terms of time cost compared to not doing that. And I really should have plotted here time to second answer, because that is actually pretty close. Like we're actually in a position that where like first and second answer are fairly similar in terms of time. So our coverage for these trace files is pretty good. We also removed, and this was like nice improvements in sort of recent Julia versions, that you can strip out more and more components from the Julia binaries to sort of reduce size and bloat. And then we also set some specific architecture flags to like just squeeze out a little bit more performance here. And then once all of that is done and all of that is deployed, we actually want to be able to monitor things. That too is a little bit non-standard. There's not so many tools out there as there are perhaps for other languages, so we had to hack a lot here. But broadly, actually, it turns out it's not so difficult. We're hoping to like that maybe eventually, maybe with us, maybe with someone else, this could be a bit more formalized. But we'll see how that goes. Until then, we basically just use a standard logger and log out in JSON, which can then be pushed to OpenSearch for structured logging. We export some timings to OpenMetrics, like in the OpenMetrics format, which is then pushed to Prometheus push gateway. Also works fairly neatly, because then we can visualize all of that in Grafana, and all of these three are standard DevOps tools. And then here we see an example graph, and these are sort of like the stages of our process, and we can really monitor how much time each process takes. So if something goes wrong and suddenly we have a performance degradation, we can really see, okay, what component broke? Is it pre-compilation? Is it just runtime? What do we need to debug? What do we need to change? We get really sort of real-time feedback on that one. And yeah, so that is sort of all of the components put together. And now I hand back to Cedric for sort of a small example of how this all can look in total.
Thank you. So we wanted to really talk about all of the different components that are needed to actually deploy an application in Julia and go in detail about, okay, how do you interface with AWS Lambda, for example. But we just don't have enough time to talk about all of this. So instead, we thought we would make an example project available so that you can take a look at it in greater depth after the talk. So it's essentially just a project which showcases a fully deployed Julia application with some very basic logic, but at least with all the components that you would need if you were to deploy your own application. So the idea is that then you can take this and take some inspiration from it, learn from it, and tweak that to your own tech stack. So it's a fairly simple application with 3 endpoints, one being some kind of test endpoint, the second being an endpoint that might allow you to test the peak floating point operations of your worker. I don't know, maybe you want to do that. And then the third point would be about just the application logic. So let's say you have some eval endpoint that evaluates arbitrary code. That might be the application logic. Of course, don't do that in a real application. And then to query any of these endpoints, you just use curl and query any of these URLs, and then you're done. You get the answer returned, and that's it. It's all deployed and answered your query or your So how does it look like? Well, first we provide a few different components for you that you can take a look at, which are quite useful. One is all of the pipelines that show the different stages for deploying, for essentially building the Docker image and then using some infrastructure configuration to deploy that to the cloud. Then you have, for example, the Docker file to really see how do we deploy, how do we build a Docker image for this application, and including any solutions that you had to use to reduce latency. So here we also build a system image. We essentially just install Julia, the repo, build a system image, and that's it. Then you have infrastructure configuration files. We use Terraform, which is fairly standard to describe all the infrastructure resources you will need in a text-based format. So it's much easier to manage, and you don't have to click through GUIs, for example. So here is one such file to configure the Lambda for deployment. Then you have the source file, which contains all the integration with the AWS Lambda runtime, which you would need to re-implement yourself, because as Stefan said, we don't have any such solutions for Julia supported by AWS. And then we have also a test suite that emulates some of the components that you would typically have in a deployed environment, so that you can at least test your application, make sure that it works, and when you deploy, you don't have nasty surprises. A nice side effect of testing that also is that when you build a system image with all the test suites run as a pre-compilation execution file, then you also get traces, so you can make sure you compile all of the parts that you need to reduce the latency to a maximum. And then, of course, you have the GitLab CI file you can take a look at. We have a basic testing job, but mainly a deployment job, which again builds the Docker image and uses Terraform. And we have the auto formatter that we set up for this repo, because why not, which Stefan talked about. All right, so to conclude, we essentially presented the way we've been using Julia at Planning Space, how we used it. Then we went on about describing a few pieces of tooling that we developed to facilitate our workflows and different issues that it solved. And then we showed how we would go about deploying a production app with Julia, but notably making available an example project for you to take a deeper look at it. Before I finish, I will mention that we are hiring a Planning Space, so if you might be interested in talking with us, please don't hesitate. We'll be happy to hear from you. You can scan this QR code and see the job openings. Otherwise, if you have any questions, you can come and see me or Stefan. We have also Luca and Theo and JuliaCon this year, or just email us at talents@planningspace. Thank you all. Any questions? Yeah.
I think this should work. Hello. Hi. Thank you very much for the talk. So I have a question on the way you structure your entire code base. You said you have a single repo and you just have submodules, right, instead of packages. So does each submodule have an API? And what happens if different people working on different parts, and if some API changes, Like since they are not packages and you don't have semantic versioning, how do you deal with that?
So we don't have an explicit API beyond what is imported, what is exported. It's meant to be quite flexible. And so you can just read, OK, we have a submodule, it uses that, exports that. And then people would typically make changes to maybe different submodules. We don't have, like the whole point was that we don't need to have an explicit API as you would with packages, for example. And so there we can actually just recode, we write some bit of documentation, and that's worked well for us.
OK, thank you.
Hello, I have two questions for you. The first question would be, with the advent of Julia 1.9 and precompiled tools, do you think they may be able to reduce or eliminate the sys image? Second question would be, if you can go into more detail, what problems you found with Amazon Linux. Were they Julia associated, or were they more on the AWS side?
Yeah, so the 1.9 changes we haven't fully tested yet. So all of this system image machinery was built before then. And we've benefited from the 1.9 changes on parallel building, because now actually system image can be partially multi-threaded. So we've seen a bit of a speed up there. But in terms of using package images that are now available, there we have some ideas, but we haven't had time yet to actually focus on this, because the current system works well enough, and there's other things that are not working well enough. So we've been focusing on those. In terms of working with AWS, it's reasonably well. Like it works reasonably well. I think the main problem really is like hidden. It's like things here and there. For example, I was saying like we couldn't use Amazon Linux 2, which is the standard operating system for Docker images in AWS on AWS Lambda, because that ships with GCC from 2017. And if you want to build system images, maybe outside with a multi-stage build, then suddenly you're actually using a more modern GCC, and then things suddenly break in weird ways. Yeah, like it's basically like broadly, it all looks like it should be relatively easy, but then in the specifics, it sometimes gets a bit weird. Yeah.
Thank you.
Any other questions? All right, let's just go downstairs. Which one?
When you showed the application startup time, did that include the time to spin up the Docker image?
So the bar graph was from local experiments from me. So that's not. So that's like we basically have some we built it so that we could mock it locally. So that's where the results are from. For the Lambda, we have what is called provision concurrency. So we always have a few hot images running. So they're currently fairly quick. In terms of startup time, it is reasonably fast. Like when we do experiment with this a little bit, we're talking like 10, 15 seconds to realize that it needs another one, spin one up, and like the init function. Most of that is actually loading the system image. Like I don't know if you've ever built a big system image, but when you do, and then you start off Julia with this big system image, it takes a couple of seconds longer than usual to start up, and that's I think where most of the time comes from. Yeah, I think we're also running out of time. Like I don't know if you have time for more questions.
Fine, we're good. Okay. Any other questions?
Could you elaborate on the Spark bar plots? If like the scale of absolute time of the whole application is?
What the scale is. So here again I normalized it because I did it locally, but we have a hard cutoff time of 30 seconds. So we have a hard cutoff of 30 seconds, and what we usually find with our queries is that if we don't do this well, we run around like 35, 40 seconds, which is just a little bit too long. So like basically, yeah, so the bar that you see here, that's one, is like sort of around 30 seconds-ish. And then when we actually do it well with the trace files, we're talking like 5 seconds or less to get back on a query, like for the first time.
Okay, thank you.
Okay, any other questions?
Okay, well, thank you both, and thanks to all the speakers and the audience for a great session this morning. I'll remind you that there is a picture being taken at 12:30 out by the food trucks. As they are saying, it's going to be logistically challenging, so I encourage you maybe to get out there a little early. Okay, thanks everyone.
have a small slide here for just about me.
Oh, okay, perfect. Okay.
There's not too much you gotta say. Just like,
Okay, can you pronounce your name? Bogart?
Yeah.
Is that accurate? Is there a better way you'd like me to pronounce your name? Okay.
Yeah, it's all. I mean, people often confuse it with Humphrey Bogart, right, with the actor guy. But yeah, I don't really.
Well, how would you say it?
Bogart.
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 There's no R.
Right, oh yeah, Bogart.
Yeah.
Bogart.
Don't sweat it.
Okay, all right. I'll give it.
I'll say it anyway.
Yeah.
So it's
Okay. All right. I'll give it my best shot. Okay.
Don't worry about it. Don't sweat
Okay.
it.
All right. I'm gonna get set up over there and.
Yeah, sure.
Yeah. Okay.
Okay.
my presentation. We're just gonna see.
No, you're doing his now, man. Sorry.
We could do this presentation
we
roulette.
just drop it around and I'd fumble through package extensions and be like, okay, package.
But this is not package extension. This is
really cutting a
really a
release,
release insert. I think there's a thing like presentation roulette or something where you give it.
Yeah.
I would love that. That would be so fun.
So let's just see if my setup
One of the things you learn
is
when
then
you're in a
fixed.
conference is how to bullshit very confidently. So you just get somebody's random thing. You would be very good.
Oh boy.
Love that.
3, 2, 1, 5. Let's restart. Pause as well. 2, 3, 2. All right. Okay, that's great.
Test, test.
Yeah. He wants me to stand in front of the podium.
Yeah. You already talked to me.
Okay.
When I came in like half an hour ago, so
Yeah.
down and was like, okay, sit here.
He's a pro.
Pick up my water bag because I need to hydrate my throat.
You do great. Yeah. This is a very welcoming audience, I would say.
I hope so.
Yeah.
Big
It's
room
not
is certainly
competition.
intimidating. So.
It's better than an economics audience.
Why? Is everyone in suits and
No, they're
looking
mean.
at trays? Really?
Yeah, they interrupt you. They jump in. They belittle you. Like it's a really hostile environment. Yeah.
Why the fuck?
Yeah. Nobody should do economics.
Yeah, we must come with the cutthroat environment, I guess. Money, made.
Yeah. It's just like nasty. It's been getting a little better, but it's still like fairly hostile. All right. All right. Hello, everyone. I think we're going to go ahead and get ready to get started here. So I'm Cameron Pfeiffer. Guess I'm chairing the session. Hello. So we're going to have a talk from Valentin Bagot here. I screwed up your name, but that's okay. I'm sorry. And without further ado, I'll let him take it away. All right. Thank you.
Hi. Thanks, everyone. My name is Valentin Bogart. This is my talk, running Julia code bare metal on an Arduino. I'm going to start with some small things about me. I've been interested in compilers, abstractions, optimization, and static guarantees basically since I started working with computers. First stumbled across Julia in 2016, right around when I learned about formal verification stuff in university. I'm very active on Slack and Discourse with the name Sukera. Maybe you've noticed me over there at some point. I'm also the maintainer of Propcheck.gl, a property-based testing framework. And I'm also currently looking for the next cool thing. So if what I do is of interest to you, socials are at the end. Now, before we get into the meat of things, some disclaimer and expectations. All models are wrong and some are useful. Like this great quote by George Box. I don't only have 30 minutes, and there's going to be some details that are slightly incorrect and or not fully explained. I just don't have time for everything. Everything here is also experimental, and this is currently not officially supported by Julia. This is mostly about where can we go, what kind of limitations are we running into, and what would require some kind of work at the core language level just so we can have a little bit of a better experience. But still, there's lots of stuff that does work. So even though there is no roadmap and no ETA on when any of this kind of stuff will actually work, we're here to think about where we can go with this. So also, I don't know what the audience here is like. So here's a little bit of an audience survey, just with a show of hands. Who knows about Raspberry Pis and Arduinos? At least? Okay, that's a lot of people. Who knows about operating systems and or firmware development? Okay, quite a few less people. Compilers and how they work a bit. Okay, there's the compiler crowd. And finally, Julia internals specifically. Okay, there's some people out of themselves there. Yeah. Right, for the overview, what we're going to get into, we're going to have a short introduction of what embedded environments really are in terms of microcontrollers. Then we're going to take a look at the Arduino Ethernet. What is this board? What are we going to look at with the board specifically? We're going to get a high-level understanding of the compilation pipeline for Julia, at least in terms of how it relates to AVR and the Arduino specifically. We're going to compile and run some code, because, hey, that's what I'm here for. And finally, we're going to talk about what does work, what doesn't work, why doesn't it work, what can we do, how far can we go, what do we need to fix, right? Okay. Now first, what really is bare metal? Let's establish a bit of a baseline there. Bare metal really means running on a chip directly. There's no operating system. And when I say there's no operating system, I mean traditionally. Traditionally, we don't have an operating system on a microcontroller, and we basically interact with the hardware directly. You do have some specialized operating systems, like the real-time operating system, or its open source alternative, the free real-time operating system, and even sometimes Linux. But generally, there's too much overhead in some kind of operating system to be actually useful in this environment. Space is very, very valuable in this environment. Power is on a budget. You are very restricted in the kinds of things you run, and you need to have very precise control on what you need to run. Nevertheless, some environments are surprisingly powerful. We have multi-core chips now, like there's some ESP32s that are very useful and widely used in the open source community nowadays. It's also becoming more prevalent to have a system on a chip where you have like no peripherals at all and everything's just on one chip. And yeah, because we don't have an operating system, everything we want to interact with, we either have to statically link into our program or we have to do it ourselves. Like no one does anything for us, we have to do everything ourselves. Yeah, so if we don't have an operating system, I mentioned it earlier, we don't have any abstractions to do over the hardware, right? So the programs we do want to run, they run directly on the CPU. There's no, usually at least, no memory management for us. There's no caching, there's no paging. It's just direct access for all the things. There's no default abstractions for anything. We do really have to do everything ourselves. No interrupts are handled. We have to write interrupt handlers. If we do want any kind of power saving functionality, we have to explicitly tell the chip, go into this power saving state now. There's nothing that does that for us. If you want to learn a lot more about how to go from the bare metal stuff to actually running a Linux system, I can highly recommend the cpu.land resource. It's a very, very well-structured overview from going from the low level up to whatever you want in a Linux system and what you require. Right. Now that we have a little bit of an feeling for what I'm talking about here, what board are we talking about? And this is the Arduino Ethernet. It's a very old chip by now. It's a small variant of the Arduino Uno. It basically has very, very, very few resources. It's got 32 kilobytes of flash memory. So this is all the program we can ever store is like 32 kilobyte. It has 2 kilobytes of SRAM. Compare that with a desktop system where you have gigabytes or sometimes terabytes if you're really, really into this kind of stuff. We also have 1 kilobyte of EEPROM where we can only read from, nothing to write to. But on the other hand, we also have some kind of low-level functionality. Like we have some serial interfaces, we have some timers, we have I2C if that's something you know about here. And yeah, anything we want to do in this chip, it's basically hardware interaction again. This chip as well, the ATmega, specifically the ATmega 328P, that's the purple one right next to the Arduino logo over there. It's an 8-bit system, so there's more or less nothing that we want to do with 64-bit can be run on there. Well, it can run, but we have to do software emulation for it, so that's a bit of a pain. This chip in particular also has the LAN chip, which is what makes it the Ethernet with a like 100 Mbit LAN connection. And the amazing thing that I think is cool of this chip, it's very, very power efficient. It just runs off a 5-volt USB, which is how I'm using it most of the time. Now, why this chip and board specifically? It has a very well-known and documented architecture. It has a very well-known tool chain. Like the AVR suite is very widely used in this community. AVR GCC is well documented and well supported. The AVR LD linker is something that I also use in this project for linking all the kinds of things together. Maybe most importantly, there's an LLVM backend, because Julia actually requires this kind of LLVM backend to be able to compile this in the first place. There's also lots of existing libraries and implementations for any kinds of peripherals or the chip itself, which is very important because if you don't have something to compare to, you're basically having to reverse engineer what the chip does, and that's kind of bad. Right? If you want to have some kind of guarantee of what things do and how you get there and what you want to do with them, you want something to compare to. Unfortunately, nothing in Julia, of course, but C giving some assembly is already plenty to compare to. And for me personally, the most important stuff, I already had it, so there's no economic cost for me. Now, we have now figured out what are we talking about here in board-wise. But what does running some code actually mean here? Like you may be all familiar with Julia being like this HPC environment, and hey, I'm running this on big clusters and stuff. But I already said earlier, we have 2 kilobytes of SRAM. We're never going to fit Julia itself on this, right? There's just not enough space. So Julia, when it compiles stuff, it more or less always goes through this kind of pipeline. This is very high level. There's some details missing, of course, but we generally start with some parsing and lowering paths where we have all our syntax tree creation, and that's where macros do their thing. And we have some type inference state that runs the type inference on it, where we say, okay, these kinds of objects have these kinds of types, they go there, these kinds of operations happen with them. It's also where static dispatch then happens, where we say, okay, we already know the types for this call, so we can just maybe just inline that stuff. We have some IR optimization on the Julia side at least, with some minimal dead code elimination, some loop unrolling there already, with tuples in particular. And finally, we then pass that kind of optimized IR already off to LLVM, where we have more LLVM-specific passes, and then compile that down to some native code, which we then run at runtime. Of course, the runtime then can throw exceptions, has some dynamic dispatch potentially. We could also have some function calls or like memory management with GC. And some of these stages can then, of course, call back into earlier versions of this pipeline, where with eval we can go back to the parsing stages, and with just regular dispatch we can go back to type inference perhaps. So this is what we usually act in when we say, okay, Julia isn't like this kind of JIT mode or this ahead of time compilation mode. Now, on AVR, the kind of difficulty is that this runtime environment is very isolated. I mentioned again earlier, it's 2 kilobytes of SRAM. LLVM alone is about 300 megabytes. So that's an order of magnitude and then some that we just can't fit physically on the chip. It doesn't fit. We can't compile stuff on this chip. It won't work. At the same time, the runtime itself is about 70 megabytes, at least on my system. That also doesn't fit. So the execution environment here is basically whatever we can compile, and that doesn't use the runtime for this point. There is some stuff we could do with some communication with a host system where the compilation happens. This is something that could work with some hot code reload if the chip and the Arduino does support that, with some hot code reload. But then again, when would you want to do this? Because, hey, if you need an attached online system to run the code on, you could just run it on that, right? So even with this kind of strong limitations where we then can't have an eval, we can't throw exceptions, we don't have dynamic dispatch because we can't compile things, we can still get quite far. It works surprisingly well, apart from some minor issues, as we'll get into later on. And yeah, the general issue behind this kind of mode and this kind of execution environment is static compilation and cross compilation. These are the two things that are more or less required, and even without actual support for that, we can still get quite far. Now, all of this is built on the wonderful GPU compiler. A huge shout out to Tim Besart for building this kind of stuff. It's a wonderful package, and it's basically powering every GPU stuff that's running anywhere in the Julia ecosystem anywhere. So huge shout out to him and them. GPU compiler itself reuses the whole Julia codegen and the compilation environment for it, and all the front-end stuff, so there's a lot of reuse of functionality there. And it even has support for custom LLVM passes, which are in some cases quite useful for this kind of work. I've wrapped the GPU compiler stuff in AVR compiler, mostly for some sanity checking reasons, because, well, I want to run JET because I want to catch these dynamic dispatches before I would try to compile things and give a nice error message, that kind of stuff. And also for some quality of life things, like caching some artifacts and being able to say, okay, I can roll back to a known working version from like 2 hours ago, which, again, very useful for debugging. If you have a working thing to compare to, you can figure out what the differences are. Now, what's the most basic task you can do in a microcontroller if we want to get to, hey, what do we run here? The most basic task is basically just toggling an LED, right? You want to see something blink, something happening, at least anything on the microcontroller, and that's the most basic thing that's specific to this execution environment. The LEDs are generally hooked up to a specific pin, and a pin in this context is just a bit in a single register. And the whole the register as a whole is then a GPIO port, is what it's called. The LED on this board is specifically hooked up to pin 1 of port B, of the RT-Mega, that's the chip there. And the basic requirements we want for interacting with this LED is we want to write a value and read a value, and that's more or less it. So how can we do that? Well, the game plan for this is that we need 2 registers. One is the port B register itself for setting and writing the values we want to set the LED to. And the other is the DDR-B register, so-called data direction register B, which basically just says, do we want to read a value from our port, or do we want to set a value to the port? It's just a direction in which the I/O goes. So these registers are generally mapped to some address in SRAM. And this memory mapping is very common nowadays in embedded development, in part because of C history, where in C, as you may know, everything is a pointer. So that's what got stuck with the execution environment. And so what we want to emulate there is basically have a pointer to those addresses, and then just store and load values from them, right? So for the 2 registers that I care about here, the port B and DDR-B registers, that's the address 25 and 24 in hex. I just put it down here, and specifically because we said it's pin 1, that's the bit 1 over there. It's unfortunately 0 base because, hey, everything is C again in this world. Now in the first naive implementation, this may look like this. We just have a main function for this, and we say, okay, our DDR-B register is a pointer to a uint8 because, hey, it's an 8-bit architecture again, and it's just at this address. So we want to write something there, right? So the 36, because Julia just takes it as a signed integer, unfortunately, the 36 is just a hex 24 again. And once we want to write this, hey, we should be happy. Unfortunately, it's not that simple, because LLVM just sees a pointer store, and LLVM is free to say, hey, you don't ever read from this again, so I'm just going to delete it. And that's a bit unhelpful, but what can you do? So there are not enough semantic guarantees from unsafe store to just be able to say, okay, I want to have this side effect of the register being affected there. We need something stronger. And the stronger thing we're looking for here is volatile semantics. You may know this from other programming languages. It's mostly known in C world, but the general semantic we're looking for here is don't ever delete the read or the write from this pointer, and just don't reorder anything. I want this to happen exactly at this point. Julia does not expose this, unfortunately. But Julia does expose LLVM call, and we can write LLVM IR directly in line with the regular Julia code, have our volatile loads and stores in there, and just have it that way, right? So Julia doesn't really expose it itself, but it gives us the tools to do the thing we want to do in the first place. So we actually want to do the LLVM IR inline and be rescued that way. So what we can do here is have a volatile store function that just does the LLVM call for us with some LLVM IR here, mark the store itself as volatile, giving us exactly the semantics we're looking for, because those are the same semantics from C we need. And then just pass our arguments, rewrite our main functions to use those volatile functions instead of the unsafe functions. Still unsafe, but volatile this time. And hey, if we compile this now down, we're gonna get our stores back. So that's great. LLVM doesn't maliciously comply anymore and just delete our stuff. This is great. Now, volatile store is good to be able to use, but it's not really a nice interface, right? Nice interfaces are, to me at least, the bread and butter of Julia. It's good. Julia is good at abstracting away things that are pretty zero cost. So what I've then done after this is say, hey, I'm just gonna wrap these kinds of volatile stores and register definitions and all that stuff in a new package, AVRdevices.gl, which gives me chip-specific definitions for the registers and some kind of common functionality, right? So a register, for example, can just be regarded as it's a pointer to a value of a given type, because, hey, we need a specific size for this. And then we can just say get index and set index as a volatile load or a volatile store, and we're going to be happy about it. That's great. Now, we not only want to have these kind of nice objects, we also want some delay functionality or some kind of other common functionality. So this is also provided by the package. And we can also have some device specifics in the submodule for saying, okay, some register that we know the type of and the name of, We can use that to build a type-safe interface by just defining some constants, which are like, hey, these are the constants we want to work with here. Now that we have some kind of nice abstraction to work with, let's build something about it. And let's go back to the blinking kind of example. If we want to say, hey, we have some get index and set index, we can just write the same code. And it's very high level now. And we basically can just say, hey, set our data direction to write stuff out on this one pin. The other one's set on to reading. And then we just have our loop. And the loop just goes, hey, write a value, wait a second, write a different value, wait another second. There's, of course, also an alternative. If we don't want to write the whole register, we can also say just write a single register, which then does a load, masks stuff out, and then writes it back out, which leads to some different assembly. And to check that this is truly zero cost, we can also just check the compiled code again. And the compiled code is a happy path. We have just a store and then really more stores. This is, of course, not the whole code, but all the get index and set index and volatile function calls and stuff, everything is inlined as usual because Julia's happy about these kinds of optimizations and just does it for us. And that's really great. And the alternative down here, as I mentioned earlier, there's just a load, then we mask the value in, and then we write it back out again. Exactly the kind of semantics we'd expect of this kind of stuff. And if we then compile it, I have this example here. Let's just have it run and hope that it just does its thing. Please be happy with me. It is not quite happy with me. But yeah, over there we have the code again from the presentation we just had. Down there we just have a close-up view of the LED. The LED is the dark one above the currently on power LED. And then over here we just have a Julia REPL with the compilation process. So basically it's all just loading the compiler package, loading the module, building the module with doing some static checking with jet.jl. Because, hey, we want to be notified of stuff early that can go wrong. It just built it for us. We just flash it down to the microcontroller, and as soon as we do it, hey, the LED is blinking, right? So that's something. Thank you. Now, what else can we do, right? Well, I mentioned that Jet is happy for all of our things. So anything that Jet can find ahead of time saves us hassle in debugging assembly. No one wants to debug assembly. That's just a pain. No one wants to do that. So for example, if we accidentally use the wrong constant, which would have the same numeric value, but we get the wrong constant, which could lead to some issues if that constant changes at some point, Jet will warn us about it because we wanted to build a type-safe interface, and Jet can say, hey, no, you're doing something bad. Don't do that. So catching errors early, very important for this kind of stuff. Now I mentioned that Hello World is more or less the string thing, well, the LED thing. Usually Hello World is more of a string thing where you print a string, but strings are really hard. It's the same thing with arrays, unfortunately, because they are more or less, there are some situations, they're more or less always stored as a global value managed by the garbage collector, and forcing the currently running session to just take those values and emit them in some compiled unit is a bit difficult and strewn with problems. But yeah, that's something to fix. But nevertheless, some global constants can work. I mentioned earlier the registers, those are global constants, but it's a bit situational. We have I've encountered some issues with tuples. There were some unrolling issues where it unrolled to the correct length, but only the first value was actually used because of some weird out-of-bounds kind of stuff. I wasn't able to replicate it just before the talk, so maybe that got fixed in some Julia version. Mutable globals don't really work because, hey, those are again tracked by GC, and getting that out is a bit difficult. In regards to the arrays, though, there's this new talk about a buffer type. That could certainly help with that. And unexpectedly, mutable local variables can also work. And in fact, I'm using that for this cool thing. This is an RFID RC522 garbled mess. It's an RFID development board, which is the kind of stuff you maybe are used to with checking into some buildings or just tapping your credit card somewhere or something like that. Same kind of technology. Don't use this specific chip because it's been deprecated through security issues, but hey, Again, old chip, well documented, lots of examples to replicate, easy to interact with. This specific chip is by NXP Semiconductors, good for embedded world, good documentation, which is something of a rarity, but yeah, it's another chip I had lying around, and in this case we're talking to it through SPI. So that's a serial interface that is often used on microcontrollers if you have some peripheral. SPI in this case is serial peripheral interface even, so it's a purpose-built communication node. And again, here's a small demo for that. And now I'll have to finagle with this again. Oh boy. Great. So again, there's quite a lot of code here. Don't worry too much about it. On the bottom right, we already have the setup again, and there's just an RFID card that I'm going to use over there. We can do a lot of stuff already. We set up some communication with a host PC, set up communication with the chip itself. We can initialize the RC thing remotely. We write some stuff for synchronization over there, run a self-test, and then just check some versions and want to wait for a card. So we flash it again, we want to connect with it with screen, any of our checks run through, and once we touch the card, we get another true. So full stack, we can completely abstract everything away, and it just kind of works. Right, almost at the end. So now, here's the big bad slide of solvable issues. Luckily, I haven't run into impossible to solve issues yet, so that's good. But there are some things that would need to be fixed. Like I mentioned that it's an 8-bit architecture, right? But if you have an int Julia, once the int reaches type inference, Julia already sees this as an int 64 if the host system is 64-bit, right? So that's kind of too late. That's something that would need to be solved. There's already a discussion about that. There's some ambiguities from base, in particular in regards to I/O, like all the kinds of serial interfaces that I already all implemented those subtyping I/O, and that works, but you have to break the ambiguities manually. There's no allocations because I have 2 kilobytes of SRAM, and if I'm not very, very, very careful about where and what I'm allocating and how much I'm allocating, I'm running out of stuff immediately. There's no dynamic dispatch because no compilation. It's not impossible to get that in as long as we know the concrete argument types and can then do some kind of static dispatch inline. That's possible. There's no error handling because where would you throw the error to? There's nothing waiting on anything. There's no screen or something to display it on. We could hijack the serial connection for it, but that's kind of the job of something that's higher abstracted than just running the thing itself. And finally, there's no tasks because schedulers are very, very difficult. So that's something that I'm going to work on for a very long time, if it happens at all. Now, you might ask why? Well, the core difficulties in this project are shared with regular static and cross-compilation, and microcontrollers are just a very extreme case of the limitations we usually encounter there as well. The general philosophy is, and the hope is that if something works better for microcontrollers, it'll improve situation in other areas as well. For example, easy deployment for HPC production environments and industry because, hey, a static binary is easier to ship around than a whole runtime and language support. And finally, the dream would, of course, be if you have some verified Julia implementation of something, why would you want to rewrite it to deploy it if you can just check that it's correct and then deploy that, right? Okay, now that's been quite a run through now, but any questions about this?
Testing. Okay. We've got time for like 1 or 2 questions. Here, let me bring the microphone.
Hey, I'm just wondering if you tried overriding get property and set property instead of get index and set index for using registers?
So yeah, that should in theory work just as well, as long as the get property and set property, the properties itself, if they're just known constants for the symbols. I just prefer the get index set index interface for that, but otherwise, yeah, it's just the same. Works just the same.
Have you taken a look at the R4 that came out like 2 weeks ago, like the new Arduino R4?
I'm sorry?
There's a new Arduino that came out like a couple weeks ago, the
Oh,
Arduino
yeah.
Uno R4.
No, I haven't looked at it. I'm aware that it's a thing, but I haven't looked at it mostly because I was busy with other stuff.
Right.
But yeah.
All right, I think. Okay, yeah, I'll do one more question, and then after that we have Christopher.
So this may be kind of an unfair question, but what happens if I don't want to use an Arduino? How much work would it take to pass this on to other architectures?
So because it's all LLVM based, anything that LLVM can work with, in theory, we can work with as well. Right, so it's not the kind of stuff that I've been doing here is not specific to an Arduino. The abstractions are very easily convertible to other chips as well. It's not just exclusive to Arduino, it's just what I had on hand. So, yeah.
Okay, please welcome me in joining Valentin for this incredibly awesome talk. Okay, so next up, we're going to have Christopher Carlson talking about making a Julia release. Yeah, I hope you enjoy this one also.
Thank you. So yeah, today I will talk a little bit about the steps of making a Julia release. And it's quite an important part of Julia because that's how actually things that have been worked on get delivered to users. So who am I? Well, I guess you could call me the release manager. I don't know, I work a lot with the releases, and in some sense I manage them, so I guess you could call me a release manager. I've done that since approximately 1.0, and I at least try to ensure that the releases that you guys get are of high quality, so with respect to both performance, but of course also correctness. Since I started with this, I counted, it's been about 27 pre-releases, 30 patch releases, 9 minor releases, and fortunately 0 major releases. And the goal of this presentation then is to give a little bit of insight into this release process. What are the current bottlenecks and maybe some things that could be improved. So first I just want to show a little flow chart here of the phases that the release process goes through for a minor release. And I will go through this in a little bit more detail as I move on. But first we have something called a feature freeze, where we branch off from the current master branch, and we're saying that we're not going to put in any more features into that feature branch. Immediately after that, we create a pre-release, which is a release that you can download, but it's known that it's probably have some issues. Then what I will focus most of my talk is about this regression testing. So that's actually making sure that the release is correct and has good performance. And we also do a set of backports, which is we put in fixes back into the release branch, and then we make new pre-releases. And then we're kind of spinning here until we find like, okay, we don't have any release blockers, then it's time to make an actual release. But let's go through these points a little bit more in detail. So as I said, we have this thing called a feature freeze, and then we branch off another branch from the master branch. And ideally, we should only fix the regressions on this new branch. There's some leeway, like let's say some feature has been open and it just didn't happen to get reviewed, but we really want to get that in. That can go in if we're kind of early in the process. If there's some very low risk, but things that are very high impact, they might also go in there early in the release process. But ideally, we don't want to get new regressions onto the release branch. It should also be strictly improving there. And that's sort of the idea. And all the pre-releases and the actual release is sort of made from this branch. So the whole point about this is that we let master do its crazy things with crazy PRs, and there I have something a little bit more stable that we can iterate on to make it more solid. So what's a pre-release then? Well, that's kind of like a normal Julia release, except we know that there are some issues with it. Maybe we know there's some performance regressions or some correctness regressions. But the reason we put out these anyways is to allow for easier testing by the community. So it's much easier to download a binary than to build from source. This also plugs into Julia Up, so you can do, for example, now if you do Julia plus alpha and you have Julia Up installed, it's going to give you the 1.10 alpha release. And you can also use these pre-releases on CI, so if you want to test your packages and so on there. Early on, we only made pre-releases when we had these release candidates, and a release candidate is a pre-release, but we think it's probably good, but we haven't tested it enough yet. But we kind of changed that now, so now we try to get out pre-releases very fast and also more frequent, because if people can test the sort of the newest state of the release branch, then we get better feedback from the community. So now we're at the regression testing part, and first I'll talk a little bit about the performance part of regression testing. And of course, ideally, the code for the new release shouldn't run slower than the code for the previous release. That would be a bit sad. That happens a lot with many software that I use, that I download a new release, and it's slower or worse somehow. And we try our best not to make that happen with Julia. And for performance, we have a quite large set of benchmarks that's found in this repository. So we can go here quickly just to see how it looks. So we can see we have different types of benchmark, arrays, broadcast, and so on. I'm just going to go in one of them, dates. Then we have the dates benchmark. And in there are a bunch of different, here it has to create some dates based on some things. And all of these benchmarks we can run by issuing this nanosoldier command. So I'm telling it, run all the benchmarks and compare it versus the 1.9 release. And then after some time, I think it's around 6 hours, this bot is going to reply to me, okay, I ran the benchmarks, now you can look at the results here. And just to show you what a typical reply from that would look like, it looks something like this. So it's telling me, okay, you ran a benchmark between these commits. And then it lists all the benchmarks here that had some small change in it. And if I scroll here, you can see there are many benchmarks that had some small regressions. And it tries to be like, okay, if I'm within 5%, then I'm not going to report it. So here I was over 9%, so I report it. But this is likely just a noise error. And one issue we have, as I'll talk a little bit on, is that there are very many benchmarks. So just statistically, we're going to have a lot of false, both positives and negatives. But with some experience, you can kind of just scroll through this and get some kind of sense where the release is. So here, one issue here would be this benchmark here, which had a 2 times runtime regression. And this is one of the important benchmarks, because this is in the problem set. So this is actually running like a full thing. It's parsing JSON. So it's doing like an actual job. It's not really a micro benchmark. And if that is 2 times slower, then I'm pretty sure that would be definitely noticed in many cases throughout the package ecosystem. But some issues that I have seen with this performance regression testing is that we have a little bit too fine-grained benchmarks in some domains. So there are very many benchmarks. So we get a little bit of noisy results, and it takes also quite a long time to run it. One thing I know other programming languages use is to not actually look at the time things take, but they look at sort of like the number of instructions things to run. So that could be an idea. Maybe that would be a bit more stable. We don't have a good time series view. So if someone misses a benchmark that gets slower, then the next time we run the benchmark test, it's going to compare against the slow version. But it would be good to have a time series view where you can follow the benchmarks over time, because then you're going to see there's a regression there, and you can track that over many releases maybe. And also if things are very slowly getting slower right now, it might be hard to detect that. We don't have that many latency benchmarks, so time to first plot and so on. But it has gotten better lately. So we have some inference benchmarks, and also package loading time benchmarks are on the way. And I give a shout out to Shuhei here, who has worked on adding that. And then we have the second part of regression testing, which is correctness. So I'm not going to talk about the standard Julia CI here. That's sort of assumed to be green. So we're passing all the Julia CI. But we are doing a bit more than that to check for correctness regressions. So we run something called PKG eval, and what that does is run all the tests on all the registered packages. And some packages are hard to test. They might require like a special binary or some secret, or PKG eval only runs on Linux and it runs in a container and so on. But every day it actually runs and tests all packages. And we can see here how the number of packages are increasing. We can see the number of passed packages are increasing. And this sort of shows the ratio between passed and failing packages. And you can see here when we have some kind of a bad regression, it takes a pretty harsh dip here, but then usually it's fixed quite quickly. And to run this for a release, then I can again ask this bot to say, run all the tests for all the packages and compare it versus the previous release branch. And it gives me a list of packages that fail on the upcoming Julia version, but that passed on the previous one. So it's like things that sort of got worse. And it also gives the PKG test logs for all those packages. So as an example of what I get from that, it shows me the packages that crashed during testing. In this case, it was quite a lot. Packages that started failing. So here's 400 packages started failing. And I can go in and look in one of them. And I can see something failed there. An expression evaluated to a non-Boolean on the latest Julia version, but it didn't do that on the previous one. And the job then is to kind of go from all these test logs to identifying Julia regressions. I would say this is a little bit of a noisy process. Like a large number of these new test failures is not really not really Julia regressions, and I'll show some possible examples. So one common thing is that packages uses internals of Julia. I mean, we kind of have this thing about the public API and the private one. That might not be as, as a hard line between those two as many people want, but at least that is one thing. And there's a thing called Hiram's law, which basically says that if you have enough people using your things, any change you do is probably going to break some people's code. And that's pretty obvious when you look at this. You can have like the smallest changes in Julia, somehow it's going to break someone's code. But Julia does not have this private public access modifier, and you can just tab in the REPL and you get some nice field there. So it's very easily to kind of accidentally start using an internal thing. This tends to be okay as long as the package author sort of is actively maintaining the package and upgrade it for every Julia version. But there's been cases with very popular packages that uses a lot of internals, and then the author kind of goes away, wants to do something else. And then when we upgrade a new Julia version, we have all these popular packages that are failing, and there's no one there to upgrade it. So it's a little bit like with great power comes great responsibility here. Like, try not to use internals, and if you do, it's kind of up to you to make sure that you fix it for new Julia versions. Another thing packages usually do is testing stuff I call metadata, which is things like inference, the number of allocations, how long time things take. So you can do sort of a test inferred to check that, okay, my code is inferred. And inference is often very important for performance, but sometimes it's also a little bit relaxed for maybe significant latency improvements. Checking how much allocation some code take. You don't want to have more allocations, but sometimes you can have performance improvement by adding a little bit of allocations. So in that case, this code would fail, even though maybe the situation is not really worse. Testing things like how long time something takes is always a little bit iffy, because on PKG eval, it runs things very, very parallel on shared hardware. So it might be very, very slow for one package. So things, the time things take can be very slow there. And it's kind of hard sometimes to decide if these things should be breaking changes, and it's a little bit case-by-case basis, I would say. Another thing people do is a little bit too strict accuracy test. So maybe you run your algorithm 100 iterations and you test the residual is smaller than some number. But very small changes to different algorithms or functions, like let's say the special functions, can cause small variation in these numerical results. So, and also changes in the random numbers can also cause many test failures. Like you just create a random matrix, you run your code, and then you just check, oh, I got this residual, I'm just going to assert that this residual will always be smaller. So I would say that this type of accuracy test should be robust enough to handle changes in random input data and also small numerical changes. So I put a little thing here where you can see the number of packages that passed dropped pretty hard. And we think this was when we changed the random number stream to, so we got different random numbers here, and immediately quite a lot of packages started failing. Something else people accidentally do is sort of accidentally test the base functionality. So a common way people testing how things are printed, and then maybe they want to test that their type is printed somehow, but then they accidentally check how an array is printed. And in one version, we changed the type of an array to get printed from this to instead be printed as a vector. And then your test will fail if you accidentally included that part. And doc tests often hit this issue because doc tests are they're designed to check the textual output. So it's a little bit tricky there. I'm going to skip these because they're not so important. So very quickly, I thought we would do a little regression quiz here. You would have to take on the role of a Julia package manager and decide, is this a breaking change or not? So I have a few examples here. So here we have a package, Yoda. It fails to compile on 1.10 because slot is not defined. How many people say this is a breaking change? No one? How many people say this is not a breaking change? Okay, most people. Yeah, so I would say this is not a breaking change. The slot type, if you don't know, it's very internal to the compiler, and it uses some compiler plugin tools here. So that one is not very hard. Here's another one. We have JSON3. It checks that when it prints something, a named tuple type here, it checks that it starts with this part, but now this starts with something else. So how many people say this is a breaking change? One person, two, three. How many people say this is not a breaking change? Okay, many more people. I would say this is not a breaking change because exactly how a type is printed is not something you really should rely on. One more here, we have an expression, just some array comprehension here, and then it says failure error in type inference type bound. How many people say this is a breaking change? A lot of people. And I would just say, yeah, this is a breaking change. You shouldn't have a failure error in type inference when you do things. So I had maybe too many here. I'm going to jump over a few. Let's say this one. Here it's calling inferred, nullable plus nullable, and it says tuple field type cannot be union. Is that a breaking change? Yes. Is it not? It's very hard here because you don't know what the thing is actually doing. If you look at the stack trace, it's calling some underscore unsafe get L type. So maybe that is doing some bad stuff, but in many of these cases, it's just very hard to just see from the error message. You have to go in and actually check what it's doing. So the job then, as I said, is to go from these test logs to identifying possible Julia regressions. But there's way too much data to manually go through all these logs. So I have a little notebook I would show that does a little bit of this. So I'm just going to very quickly go through this. So this is a notebook called PKG Eval Analysis that I have on my GitHub. And what it basically does is that it downloads the data. And then I have a bunch of different categories here for different types of failures, test failures. So it could be like a new ambiguity, approximation error. It could be different assertions that I found for specifically this release. And then what I go through here is I have pattern matching between some part in the log and some type of test error. So if the log prints out does not match inferred return type, then it's an inferred failure. And then for every release, you kind of get these categories of different failures. And then I can check how many packages have a failure that I haven't categorized. There's many here. You can list out those packages. So then I would go in and look at the logs here and try to categorize it. You can see what packages fail with a particular category of failure. And you can sort of categorize them. We have 282 packages that I don't know why they failed, 35 that failed with this, and so on. So just to get a little bit of structure in this very, very big data set. So after this categorization, it's time to actually understand what the problem is. And as you kind of saw on the examples I did before, the sort of distance from the test failure to the actual Julia change can be quite big. So you have to sort of actually try get a minimal working example and to like provide a test case. And tools for finding what the problems is, like git bisect is often useful. There's also a thing called C-reduced Julia, which like you give it a large amount of code and you say what the problem is, and then it tries to like mechanically make that code smaller and smaller while still having the same error happening. So this is quite a time-consuming process. And one question could be like, oh, is it worth it? Maybe we should just make a new release and then people will find the bugs there when they use it. But I think it's quite important that every release of Julia is kind of like high quality. I think it provides like confidence in the project. People get more, it seems more reliable if you can sort of upgrade often and have things still just working. Okay, so then when we have identified the regressions, that's not the only thing. They also have to be fixed. And this is a little bit of a frequent bottleneck because the set of people that can fix certain issues is sometimes small. They might be busy, they might be on vacation and so on. They might have other things to do. And sometimes fixing very tricky issues can introduce new regressions itself. So then we have fixed one thing, but then up pops another issue. So that can also be a little bit of a bottleneck, like you think you fix something and then something else comes back. But having these good minimum working examples, in this case you want the minimum non-working example, I guess, because it's a bug, but that usually helps. But anyway, when things are fixed, they get merged into master, and then afterwards we take those commits from master and what's called backporting them to the release branch. And then, but backporting things sometimes gives you merge conflicts when the release branch looks quite different than the master branch. And that especially makes backports to the LTS release tricky because a lot of things have happened since the LTS release, and the fix on the master branch might look very different from the fix you would need to apply on the LTS release. Anyway, let's say we've spun this thing over and over. We don't have any release blockers. So now we're at release time. So we have had the release candidates out for a while. People have tested it. There hasn't been any new problems. So we're kind of high confidence that this release is good. Then there's a similar process to releasing a pre-release. We upload binaries. We create the release on GitHub, announce on Discourse and other places. And we usually now also have a highlight blog post with the release. Then after that, it's just waiting. And this is me when everyone is trying it out. It's kind of scary because you try to make sure everything is good and so on, but you never know if something sneaked in the end. And the best feeling for me after release, if it's completely quiet and there's nothing happening, that means everything went well. That's sort of the best way. And if people are posting things like, oh, look how better this thing became, that's just a bonus. But yeah. A little bit what can be done to help with releases if you want to help out. One very useful thing is to testing pre-releases. You can use them locally as a daily driver for your own stuff. Probably not for your production stuff, but the things you do locally and try find issues. You can run your package CI on pre-releases. You can report issues, create minimum working examples, and sort of help out finding what the issues are. If you want to go a step further, you can look through the PKG eval logs maybe and open fix issues. And if anyone is interested, I'm happy to get some help with this notebook I have. Maybe there are smarter ways of doing things. And one thing I thought about is like AI to the rescue maybe. Like we have all these logs, and I'm not good at all at this stuff, but maybe someone is. Like if we could somehow take all these logs and have something automatically characterize them somehow to like find what are the things that are similar between the logs and make different categories. That would be very useful. So yeah, that was it for me. Thank you.
Okay, thank you very much. We have time for some questions. Who's got some? Anybody? All right, we'll do Lily.
Should packages run CI on master as well as pre-releases?
So the question is if packages should run CI on master as well as pre-releases. And in my opinion, I would say yes. There's no harm in doing it. In the worst case, you can just ignore the results of it. But if you want to, you can actually see, oh, things are failing, and then you can help out why. And I mean, the only way that we figure out things is either through PKG eval or that someone reports it. But it's always easier to get things as close to a regression to get it reported, then it's usually easier to fix it. So if packages were running things on master, then we might get bug reports even earlier. Of course, sometimes master just breaks a bit randomly, but it's totally up to you how serious you want to take that. So I would say if you're interested in helping out, then running things on master would be helpful. Yeah.
Yeah, thank you for the talk. Quick question on the previous slide about kind of the next steps to the future. I love that your Hacky analysis notebook, actually, and I think it's a really fantastic idea. I was just wondering, do you think it would be a useful community resource to maybe turn that into some sort of dashboard that people could navigate through as a community? Because I actually didn't even notice that you could look at the package eval logs, for example. So.
Yeah, so the question is if it would be good to have like a dashboard thing around this, and definitely having some more, I mean, if we look at the, let's see, this thing here, it's not the most pretty, so having a bit, if someone is good at like web stuff and can process this data and make a nice presentation out of it to make it easier for people to find out stuff, that'd be very helpful. Like for me, I don't know anything really about web things, so I'm just doing what I have available now, but there's definitely a possibility there for someone who knows, let's say, web stuff and wants to help out a bit.
I was going to ask a similar thing. The benchmark reports are totally unreadable to me. I know you guys have trained yourselves to do it, but every time I look, I'm like, what's going on here?
Yeah. I mean, the thing is, like, let's say we go to scalar, for example. So it's testing like arc-sine here, and it's testing it for very many arguments, and then arc-sine hypotenuse for many. And the code for these haven't changed in many years. Many of these, some of them have. But somehow I think we need to do it so that not all of these are run. Like, I mean, you can always think like more is better, but that's not always the case. Like, there's a trade-off there between noise and signal. So yeah.
I would like to use my moderator privilege, and I'd be very interested in doing like some stats on this, because Rust has a really good like compiler dashboard thing that tracks these regressions, and I'd be like very interested in like looking at the time series for this, and like the fact that some of these are ignored by like at 5% margins or something is like you're gonna miss like long-term persistent regressions, and like it would be really nice to track those and head those off.
And I can say that all of these previous runs are available.
Oh, they're available? Oh, hell yeah, I'll do that.
So if we have the by date there, we have for quite a long time.
Oh, absolutely. So. I'll put something up for that. Yeah. I need help presenting it because I also don't do web stuff. Anybody else have good questions?
Are those historical records just benchmarks or also package eval?
It should be package eval as well, I'm pretty sure. Yeah, there's PKG eval here. And I think that's what's being used to make, I mean, you could reproduce this plot, for example, by looking at earlier data.
The question was, do they have logs too?
The question is, do they have logs too? I think so, but the logs are not stored together with those. So in my, let's see where I have it. In my notebook, I have a little code here in the beginning to see where that is. I have something called add back logs here that I run. Okay, here. That downloads the logs. They're hosted in a different place, but they should have logs, I think. Yeah.
All right, that's awesome. Okay, anybody else? All right. If there are no further questions, please join me in thanking Christopher for that wonderful. That's the last one. There's going to be a 30-minute break, and then there will be another one in this room at 3:30. That will be about the three choice files, I think. Three files here. Yeah, well, they've got like third-party support partners, Julia, and it's like great. And they're also very, so at the moment, the way I've put it, like, so when I fast forward through, for example, that was so yeah, like it's definitely moving in the direction of size. It already gives you like comparative version with parameters. If it's flexible, but yeah, they want to make it so that it's basically like the entire project is different simulations. They model everything in like software. But like you can see as far as they do efficiency, so it's not terrible. But it's definitely better. No, I've seen it, but yeah, I have like mentioned it up again. Well, you just surely have the question without having numbers. Just, yeah. So far as I can tell, there is no Srinivas in here, which means there may not be a talk, I guess. I don't know. Let's give the speaker a few minutes and then figure it out. Okay. And Srinivas, enter the room. Right. This is really good network bit about how you're gonna in a restaurant. It's like you ever be in a restaurant and they're like the Smiths, party 2. Smiths, party 2. Dufresne, party 4. No, man, go back to the Smiths. The Smiths are missing. Dufresne, search party 4. Anyone Srinivas walking down now? No.
ChatGPT, you can write the title.
Yeah. That's actually not a bad idea. Oh, we'll give the speaker like 2 or 3 minutes, and then we'll say like, okay. Not gonna happen.
Impersonates.
I don't think I got more. I can do mischief for all day long. My belt holds up my pants. But my belt was holding my belt. Who's the real hero down there? Just copy paste and get that word there. Yeah. That's not bad. It's right. I don't actually think I remember that anymore. I think the other one I got is like, why is it that I go and I buy a donut and they give me a receipt? I don't need a receipt. I gave you money. You gave me the donut. You don't need a record. Good. Srinivas. Going once, going twice. Okay. So Srinivas has not showed up for the talk, so I think we may call this, I guess. So you're welcome to hang out here. And I will not be doing any further stand-up. Thank you.
Yeah, absolutely. So let me show you. Unfortunately, not easy to find.
If you want one of those, you can. You are perfect.
Hello.
I want to thank you for coming and doing this first. Yeah, we really appreciate your time.
All right, let me see if I can. Hello.
Alan's roommate from Yale.
Ah.
Do you need any help?
Not yet so far.
Okay.
We'll see in a minute.
Looking forward to your talk.
Kind of talk here.
Yale's roommate from
Oh, very nice. Very
French
cool.
tennis. Very cool.
Ah. So this is a combination Alan birthday thing
Yes,
and
exactly right.
JuliaCon
That's
thing. All right,
exactly
okay.
right. Yes, and JuliaCon and a few other conferences too. So.
Okay. What other conferences?
Oh,
Is that-
there's another one called Jump Dev, which is an optimization ecosystem, and there's
kind of
SciML.
always nice to know who you're talking to. Okay. So who else? What other conferences are here?
Oh, there's also SciMLCon. So SciMLCon, tries to combine machine, physical simulation and machine learning. So
These are all Julia related.
yeah, it's a sort of Julia sub ecosystem kind of thing.
SciML.
SciML, yep.
So that sounds like machine learning with the ML there. Is that some?
Exactly. Scientific machine learning.
Okay, all right. Oh boy. Okay. Well, let's think. What should I talk about here? Gosh.
Virtual equation solvers combined with machine learning.
But just as a community, we're super excited.
I could put a lab on you.
Yeah, that'd be
feel better with that. Yeah.
Thanks.
I can. Yep. So I'm just gonna power lock it just to make sure it doesn't turn off on by accident. There you go. Just don't put it in the same pocket as your cell phone.
All right. Let's see what I can do here.
My advisor is somebody else.
Okay, cool. Just to make sure that they use.
Yeah.
tell the person to introduce it. Yeah.
Have any audio in either slides or presentation at
I
all?
don't know. Maybe. Probably not. Let's assume not.
Okay, I just wanted to make sure.
Well-
Yeah, 'cause I just wanted to make sure it was hooked up and everything really quickly.
I don't. It should be okay. I don't think. I doubt I'll use audio.
Okay.
Unlikely.
All right.
We don't know, but unlikely. Oh, hello.
Yeah.
Yeah.
Always good to see you.
Yes.
So you look
Happy
like you're
birthday.
busy.
No, I'm fine.
You're fine? Okay.
I haven't figured out what I'm going to talk about. I was wondering who your audience is, but
I think you should just be yourself. I mean, so for example, the plenary speakers, many of the people never even use Julia, and it's fine because the world's bigger than just one, Julia fish, right? So we're very happy about that. So I'm glad you're here. Roger, you want to take a picture of Steve? Is Steve allowed? We'll show the picture of Julia. How's Elisa?
oh, she's very well. In fact, I was going to tell a story about her at the beginning of my talk.
Okay. So I was just at Hampshire. They had just got this reunion. I had dug up. I'm moving from the book. I dug up the complex analysis work that did actually. That was exactly the problems that I used to solve. I'm not sure you remember, but those were the problems that I used to solve together. Back in the day. And
I have 1978.
In 1978, yep. Back when I wasn't mature enough to know what I was doing back in those days. Well, at least the truth. So, yeah.
She must be a year and a bit older.
I was one of the younger ones. First of all, I went to 10th grade, and I grew up in FC where if you, I mean, I'm a little bit joking, but if you could read, you could skip 8th grade. And so I skipped 8th grade because I couldn't. So I was like 2 years, at least would have been 2 years older than me, all like that. So, well, I'm 60, 62 up there.
60. Okay. That's a good question. I just want to know how old my spouse is.
So, it's not really birthday, but I have a number. So you must know, Mathematica first came out in 88 or 89? Okay, because I first came to Mathematica sometime, I'm certainly not the case, but does this name mean anything to you? You showed me Mathematica really early. It's definitely 88 or 89. I think I should. You know Bruce?
Yes, I know.
Bruce one of the first 5? I mean, I think there must have been many copies.
Maybe. I mean, I knew him fairly well. So, because he was a cellular automaton fluid mechanics.
Yeah, exactly. Right.
So, and that was.
I still talk to him a lot. I mean,
I probably haven't seen him in a couple of years, but I
probably haven't seen him in a couple of years. I've seen anyone.
Right. When did I last see him? I saw him one definite time. I saw him. He told me. He said he was the president of the American University of Edelman. He said we should visit there while he's there. So eventually, just about a few weeks before he left, we finally did visit. Even if it was one of those cases where I really had no idea anything about Armenia. I was like sitting in the airport lounge, looking up in Wolfram Alpha, basic stats about Armenia. That was interesting.
By the way, regarding your talk, so it's 4:15 to 5. I'll give a quick introduction. We'll get over to
my team told me there were 2 different times. Your people. One is for your birthday.
Oh, that is. Oh, okay. What?
Well, so one of them, actually, I meant to bring this up. I was just somebody just reminded me about this. One of them says 45 minutes, the other says an hour.
Okay, I'm pretty sure 45 is the official. Maybe. Well, I have nothing to do with any of this, just so you know. But let me just see if I can identify these two. I'm going to guess that the one that was my birthday is the one that probably was stuff because I think people did it. Okay, let's see. So this one says this is the broken one. Yeah, I don't think this was. You want to talk for an hour and 15 minutes? I mean, I feel like you never.
I don't know. I mean, look, I'll tell you what. Why don't I plan to talk for 45 minutes and people have questions?
Keep going on that. Let me tell that to them so that we know that. So would you like me to let you know when? I was going to say I was going to let you know when 40 minutes are up, but now I feel like I should let you know when 45 minutes are up.
whatever. I can probably figure it out. I mean,
Oh, you mean
So what we propose is, there's nothing in particular happening with five, right? So the proposal then is maybe at 5 o'clock I'll let you know when it's 5, and people can ask questions until the task.
and I then have to leave for the airport. So now to that. I don't really have to leave. It depends on how much traffic there is, but probably.
How hard the questions are.
Getting
the airport's easy. Getting back to the airport is impossible.
Oh, is that right?
Yeah, the tunnel's closed, everybody's back.
I haven't been to the airport in a month or two since the tunnel closed.
Yeah. All right, so at 5 o'clock, you'll see me sort of waving.
Yeah, all right, okay. I'll try and.
There's a clock back there to understand. You see
Yeah,
that?
I see. I also have a clock on my computer, right? One would think.
Does the setup look good? Anything I can help with on the setup side?
No, it should be fine.
Awesome, thank you.
I bought a little prop, which was a memory from almost 10 years ago.
I found that in my archive. Yes. It's okay,
I believe you. I actually just said to someone that I bet you have a copy handy too.
Let's see what I actually do.
I had it just upstairs in my office.
Aha, well, let's see. Look at that.
Look at that.
Snap. They match.
Surprise, surprise.
I look at peculiar and younger there, but so did we all.
We all, yes.
It's,
okay, so actually, what's good about that is I could hold this up, and you could also, since
I
you have it
could- I could prove that
since you have it digitized, you can
Yeah,
the
yeah,
audience
right.
will see it. That's actually
Yeah.
good.
Yeah.
Okay, I like it.
We met 10 years ago at the summer school.
Oh yes, I remember.
This is
Yes.
exactly 10 years ago, exactly.
Okay. So what have you been up to?
I'm working at DNV, it's a risk management company.
Where?
DNV, it's a risk management company, so I'm leading a small unit.
You
looking
worked on
into-
something to do with cracks. Am I
Yeah,
remembering
that's
correct?
correct, yeah. But I'm not
Okay,
doing
my
that
memory
anymore.
still works.
Yeah. I've been
Risk-
following what you're doing, but it's difficult to keep up that you're doing so much. Really impressive.
Yes. So, what kind of risk management for finance?
No,
or something?
same. So actually,
I don't.
if everyone could take a seat, we're going to start in 1 minute. So just a minute, we'll start. It seems like I haven't seen anyone stand. There are some great seats in the front row. But they're reserved for you. So at this point, just come on into the front row and take the great seats. Only a small surcharge. No, just kidding.
Yeah. Sure. Just thought of a different thing to say.
Alrighty, so we're going to start. And it's a great pleasure for me to introduce the next plenary speaker for JuliaCon. And as many of you know, the plenary speakers for JuliaCon represent many different languages. We're not usually snobs, sometimes. But I have to say that when it comes to mathematical languages, there really are only two that I use on my desktop right now. I was certainly not the first user of Mathematica, though I was the first user of some other language. But I'm still a user of Mathematica, and I did use Mathematica back in the early days in '89, which I just learned was the first year that Mathematica came out. And so I'm a long-term user, and I still very much love Mathematica. Quick story, I found this poster, but I know that, can I just press this over, or maybe you can do that? I was so glad to see that Stephen had a copy of it, because it would be hard for you all to see it. But 10 years ago, almost to the date, it was in September, there it is, Steve was here.
I looked at it.
And packed an audience, just like he's packing the audience now. And so, again, breaking records, for MIT talks here. And I don't think I need to say all the prizes in history, because you could find it all online. And, he's got them all, so, I'm not going to list them. And so, without further ado, let me hand you over to Stephen Wolfram.
Thanks very much. Well, first thing I think is it's a happy birthday to Alan, and I realize that I think Alan and I first met probably in the early 1990s, but it turns out my wife actually knew Alan back in 1978 because they were both at the Hampshire Summer High School Math program. And actually, Alan just told me that they worked together on a bunch of complex analysis problems. So, and my wife discovered just yesterday that she had an email from Alan from 1992 that she didn't respond to. So she's planning to get to it. Well, so, I happened to be doing a little bit of historical research recently in the last few days, actually, because I was sadly writing an obituary for a chap called Ed Fredkin, who was a longtime fixture at MIT. And by the way, if anybody here knew Ed Fredkin when he was at MIT, please find me afterwards, because I have a bunch of questions. I knew Ed for 40 years or so. But one of the things that I found as I was looking for things related to Ed is something that he wrote in 1963. And 1963 was also the year Alan was born. I thought it might be interesting to just take a little look down some kind of memory lane of what a magazine called Computers and Automation was like in 1963. So it's kind of there. There's a very, it's kind of a sophisticated graphic on the cover. The fastest outbox in the world is being advertised there, with paper tape on one side and a modem on the other side. Keep going here. That's a computer of the time. It's kind of interesting to see the span of what's happened over the course of 60 years, both in terms of computer hardware and in terms of things like languages and so on. But maybe we can keep going here and just take a look at what was in here. But I wanted to show you, this was actually the article that caused me to pick up this magazine. It was called The Time-Sharing 2 Words of Computers by Edward Fredkin. And it says here, a typical input-output station for an individual user under a time-sharing system. You can probably see that. It's kind of fun to see. So, it goes through ads for computers of the day. And, computers used to have desks that came with them and things like that. But it's kind of, and this is, that's an example of a computerized education of 2 screens. It looks like a Lisp tutorial there, shown on 2 screens of the PDP-1 computer back in 1963. But I thought it was kind of fun. I looked through here and I got to the end, and I thought it might be interesting just to take a look at what the view from 1963 of the big picture of the far future, according to Ed Fredkin, might have been. So maybe we can just read this because it's kind of fun. It says, if we assume that the development of artificial intelligence will take place, how can we form a coherent picture of our place and its place in the great scheme of things? It seems reasonable to consider that artificial intelligence is a next step in the evolutionary process. Once there was a prototype land creature that crawled out of some primeval ocean, most primitive in comparison with a more advanced creature such as the saber-toothed tiger. And once there was a prototype intellectual creature, that's us, and we will seem most primitive in comparison with what is to come. Remember, this is 1963, so it's interesting to compare what was said then with what's said now, which is pretty much the same thing. However, instead of participating in evolution by merely serving as a runner in a genetic message relay race, we can choose the great distinction of directly employing our primitive yet unique intellectual talent to the task of evolution. We have conceivably arrived at the notion of the next step in evolution by trying to fit the future development of artificial intelligence into the overall scheme of things. Joshua Lederberg, actually I knew him somewhat, a Nobel Prize-winning geneticist at Stanford University, gave some attention to the problem of guessing the characteristics of that species that will evolve from mankind. He arrived at the conclusion that it will be artificial intelligence. Now, footnote there, Joshua Lederberg worked on things like Dendril, which was an early AI-based medical diagnosis system. So he wasn't purely, I'm giving up on biology, it's going to be AI from here on out. So anyway, he says, how do we proceed with this great task? J.C.R. Licklider's position in 1959 was that we should concentrate on the development of a man-computer symbiosis, a system in which men and machines would form a close-knit intellectual team, each complementing the capabilities of the other. Then, when so equipped, we could much more effectively tackle artificial intelligence. Well, let's see. After the ascendancy of AI, it seems that mankind's intellectual skills will no longer be very useful in the solution of problems. Today, man is hardly using the intellectual capability he has. How ironic it would be to pass through our span as the dominant species in Earth's evolutionary tree without ever realizing our true potential for intellectual creativity. By means of a symbiotic relationship with the capabilities that we now know how to implement in computers, we can not only proceed with the task of creating AI, but we can reach for and achieve human creativity at a pace and level never before attained. We could advance all areas of science and art as partners in intellectual systems that complement and reinforce our correctable weaknesses and that make use of all of our inherent creativity. It ends, with computable wings, we could soar to meet the phoenix. It's a little odd. But anyway, I find it interesting that that was the view from 1963, and many things about this are still the view today. But we made a bit of progress in that time of being able to make computers and computation kind of realize their potential. maybe I can tell you a little bit of my story in trying to do that. You know, I kind of discovered computers when I was, well, about 12 years old, which is a terribly long time ago now. Let me see here. Actually, what caused me to discover computers was something that I wanted to do. I got this book when I was 12 years old, actually. I can prove that because I wrote my name and the date. I used to do that very efficiently in books I got. But anyway, I got this book, and I was really interested in the kind of what was happening on the cover of this book, and understanding, well, what the fact that you start with sort of all the balls on one side of the box, and then it kind of randomizes over time. And so my first big computer program, actually, was an attempt to simulate the balls bouncing around in a box like that. I wrote that in 1973 on a computer that looked like that with this is, I don't think this is the program that did those particle simulations, but I don't know for sure because it's kind of hard to read a paper tape these days. And it also doesn't help that that paper tape was encoded using a paper tape loader that I wrote back in those days, which that's a separate tape which I don't have. Anyway, so that's kind of what first got me into using computers. I was interested in solving a science problem, basically. And I got interested in physics, and I discovered that one of the bad things about physics was you had to do all this calculation, algebra, and so on by hand. And I thought, this is really boring, really mechanical. There's got to be a better way to do this. And then I discovered, this must have been 1976 or so, that actually people had built systems for doing algebraic computation, and I started using these things. And there was one actually at MIT. It was called Maxima, and it was you could get to it from the ARPANET. By that time, the ARPANET is the predecessor of the internet. By that time, it was I had access to those things, and you typed @0236. It was node 236 on the internet, so to speak. There were only 512 of these things in those days. And you would get to this thing called the MIT MC computer, which actually, interestingly enough, Ed Fredkin had been the director of the lab for computer science. He wasn't at that point much, but by that time, he wasn't really involved in things like Maxima. But anyway, I became a large user of Maxima and Reduce and Schoonship and a bunch of other systems that did kind of algebra by computer and so on. And that allowed me to do a bunch of physics. I was working on particle physics, and that was the late 1970s, which was kind of the golden age of particle physics. So it was kind of cool because it meant that a teenage kid could there was low-hanging fruit to be picked by a teenage kid, at least a teenage kid who knew how to use computers and knew how to do things that for some bizarre reason nobody else seemed to do, which was use computers to do mathematical and algebraic kinds of computations. So I got this kind of reputation for being amazingly good at doing things like integrals and so on. Actually, I was and probably am still really pretty crummy at doing things like integrals. But me plus a computer was really pretty good. So, you know, I worked on particle physics and things like that. And in 1979, I kind of had got to the point where I was really frustrated with all the systems that existed to that time for doing kind of mathematical computation. And I kind of talked to folks who'd worked on them, and I said, you know, you could do a lot better. And they said, well, yes, you know, the young people said, there'll never be anything better than what exists today. The older people said, well, you're right, it could be a lot better, but we're too old and tired, we don't want to do this. So I decided, okay, I'm going to build my own. And so I started in November of 1979 trying to design a sort of computer system for doing mathematical computation. Well, it was sort of an interesting process for me because I have been used to doing natural science, and in natural science, kind of the idea is you start from the world as it is, and you try and kind of drill down and find the kind of primitives from which the world is built up, and then you kind of build back up to make predictions about what's happening and so on. So I kind of tried to apply that same methodology and thinking to the design of a computer language. And what that led me to was a lot of stuff about mathematical logic. And I mean, in those days, I remember I was at Caltech at the time, and I remember going to the bookstore there and buying sort of all the books on computer science on the shelf, which is about that length of books in those days. and reading through them and so on. But I kind of went back to sort of things about mathematical logic and some of the earliest kinds of ideas about computation, like combinators, which were actually the very first method, the very first sort of implementation of universal computation in 1920. Combinators were not easy to understand, and they're still not easy to understand. So when Turing machines came along in 1936, that was kind of the moment when people really started understanding that idea. But combinators had predated them and sort of represent a very idealized way of doing symbolic computation. So anyway, I tried to study those things, and I tried to sort of figure out what is the essence of how one should compute things. And what I ended up coming up with was this idea of making transformations on symbolic expressions. And it's sort of embarrassing to say that that was something that I kind of came up with in 1979, and I'm still doing that same thing today. And it turned out not only has it supported all of the work I've done on sort of computational languages, it also turns out, with perhaps even greater embarrassment, that we made great progress in recent times on a fundamental theory of physics. And it turns out that you can think of that fundamental theory of physics in some ways as kind of the obvious thing to do, given that you have this idea of transformation rules on symbolic expressions. So it turns out there's only one idea, so to speak. But in any case, back in those days, I was building the system. It was built in a newfangled language called C. And I think I might even be able to run it here. Let's see. Let's see whether this is possible. So I built the system. It was called SMP. And this is a VAX emulator that thinks that it is, it thinks it's 1986. So let's see what happens here. I don't know whether this will work, but OK. Well, we seem to have an input prompt. Let's see whether we can do 2 + 2. Yeah, very good. OK. And then it had things like, you could say, let's see whether this works. Yeah, OK, so we could factor some polynomial or something. And there were many things about SMP that were not good ideas. It was it's very strongly based on sort of everything is about transformation rules for symbolic expressions. Oops, I forget actually how to do this. I think it works like this. I think that's right. I think that's how I define a function. And, oh, bad. Well, that's not a good sign. What do I do now? Let's see. Maybe I log out, and maybe if it will log me in again, we'll start again. I guess software rots in all these years. Oh, that's interesting. Oh, I think it thought I was looking for its help system, which somehow went missing in the intervening, whatever it is, 45 years. Anyway, among the bad ideas, it was funny because when I designed SMP, most people couldn't type. And so it was really important to have short command names because people couldn't type. And there wasn't anything like autocompletion and so on. There were other bad ideas, like there was a function called rex. Rex was a random expression generator. And so it would generate, which was sort of a good idea for testing, but it used kind of a Markov chain to generate bigger and bigger random. So I wonder how big a random expression I can generate. Let's see if we can crash it. Oh, there we go. OK. I think, let's see. I wonder whether this will work. Let me just try something which probably won't work. But let's just see what happens if I do this. Oh, yeah. OK. That worked. It was slightly... Anyway, so I built SMP. The first version came out in 1981, and it had many very interesting design ideas and many design mistakes. And it's kind of interesting to see. I started my first company around SMP, and a few years went by, and you could read kind of the training manuals that people used to train people about SMP. And one of the things where there was a section, I remember there were these things in SMP called marks. And marks were a profoundly bad idea. And you could kind of tell that because that section of the training manual, it began with marks are the enigma of SMP. And that's a design mistake. It's a very thankless job doing language design, because if you get it right, It takes a long time to see what's obvious, and when you get it right, nobody notices. It's only when you get it wrong that people actually notice. So, in any case, after I built SMP, it turned out that it had both practical kind of consequences of, okay, I had a tool I could use, but it also had kind of a theoretical consequence, which was that I kind of started realizing that you could just like start from computational primitives and build stuff. And so I'd been interested in kind of lots of problems in physics and natural science, and one of those problems was kind of how do complicated things happen in the world? And so, you know, how do snowflakes get complicated patterns? How does turbulent fluids get complicated sort of random looking stuff going on? How does that work? What's the origin of those kinds of things? And so I, at first, tried to use all kinds of fancy mathematical physics that I knew from doing quantum field theory and so on, and it just went splat, it didn't work at all. So I thought, okay, what's plan B? Well, you know, we want to have some definite models for these kinds of things. What kinds of models? How can we generalize what we do with mathematics and sort of deal with more general kinds of models? And I realized, well, okay, we know about programs. I just built this thing that was kind of starting from this idea of computation and just building stuff. Or what happens if we imagine that instead of using equations and formulas and so on, the natural world is instead using programs? What might those programs be like? Well, you know, we're used to programs that have long, complicated, you know, that are built up in long, complicated ways. But what happens if we just think about sort of the simplest programs we can imagine? So at that time, I started looking at trying to say, what happens if you just pick a tiny program sort of at random and just see what it does? So if we say, it got a lot easier to do these things since that time. But let's say this is a very simple kind of program, a representation of a very simple kind of program. It just has a line of cells, each one black or white, and at each step it follows this rule. You can think of that rule as a little program to say what the color of the cell should be on the step below. So if we say something like, you know, let's just make a let's just show that particular rule there, and let's just show it starting from starting from that initial condition. Let me just show it as some kind of picture there. Okay, this is so that's a very simple rule, and it does a very simple thing. So okay, we think we understand what's going on. Let's try a different rule here. Let's try a rule that has that bit pattern. Okay, let's try that. Okay, that rule, it's a little bit more complicated. It makes a pattern. We could keep going. It'll make a nice nested pattern after a while. But we can ask the question, well, what happens if we just look at all possible rules of this type? It's kind of a minimal kind of computer experiment. You imagine that you have this kind of telescope that you're looking out into this computational universe of possible programs, and you're just asking what's out there. So we can just say what's out there in that term. Let's pick this. Let's do something like this. Let's say let's just look at a few of these. We'll just make a table of pictures of all of those things, and we see, you know, fairly simple things going on here. This is just a nested pattern there. And then, after a while, we get to my personal all-time favorite science discovery, which is Rule 30, if you can number these rules based on the bit pattern up there. This is what it does. You started off from just one black cell, and it makes all of that complicated stuff. So let's run that up here. You can just run it. That's what it makes. So this is kind of a weird thing, because very simple rule, yet when you run it, it does very complicated things. And what I kind of realized is that's a lot of what's going on in lots and lots of systems in nature, from turbulent fluids to all kinds of things. Now, there's a lot to say about what goes on in this kind of system, but one of the things that's sort of interesting about it is one's kind of used to, in traditional kind of mathematical approaches to science, the big thing one wants to do is, can we kind of jump ahead and predict what's going to happen more quickly than just by running the system? Can we just say that if the time is 1,000,000, we fill that into some formula and we say this is what the system is going to do? But the question is, will that always work? So in a case of a system like this, will we be able to kind of jump ahead and find a reduced computation that tells us what this is going to do sort of more efficiently than the individual steps in its evolution figure out what it's going to do. Well, it turns out that this is, well, cases at least like this, and probably this in particular, are examples of a phenomenon I call computational irreducibility. You basically can't know what this is going to do much more efficiently than just running it and seeing what happens. And that's a sort of important, has important consequences for kind of thinking about science and thinking about what's possible. It also is a reason that if you do simulation, it's a reason that doing simulation is something that isn't just kind of convenient, it's something that in a sense is fundamentally necessary. By the way, I have to say, as a piece of sort of personal history, that little simulation that I tried to do on that little computer with 8K of 18-bit memory was something that I actually simplified all those balls bouncing around to something which was just a bunch of bits, which actually was a version of programs just like this. And in fact, I'm pretty sure that I ended up seeing phenomena like this, and I just didn't understand what was going on back in 1973 or so. And it took sort of more context of understanding kind of the idea of computation to be able to realize that, yes, there was a real phenomenon going on where you could have these very simple rules and very complicated behavior. But this phenomenon of computational irreducibility is a very important phenomenon. Somebody has their hand up, but what? Oh, yeah, for this, sure. That is easy to do. There you go. Sorry. So in any case, things have the most bizarre kinds of consequences. I thought of computational irreducibility as this sort of piece of basic science that gave limitations on things in science. I think it eventually became the inspiration for bizarre things like the proof of work idea for cryptocurrencies and things. Lots of different consequences, lots of sort of stuff in philosophy about implications for free will and so on. It's a long, complicated story about what's happened with computational irreducibility. But for me, back in those days, I mostly saw this as being kind of a fundamental sort of result about how computation works out there in the computational universe, and that kind of initiated a whole process of thinking about how to make models of things, not with equations, but with programs. And I wrote this big book. It came out in 2002. That was the thing that I was talking about in the talk that Alan invited me to, the last talk that Alan invited me to give. Kind of the idea at that time was there's this way of generalizing modeling things that uses programs and so on. And a lot of people at that time said, no. Mathematical equations, they're great. They're going to be the future forever, so to speak. It is interesting to see that in the last 20 years, when you look at new models that have been produced, the vast majority are now programs and are defined by programs and not by mathematical equations. Well, in any case, after I worked on basic science for a while, I went back. I've kind of alternated in my life about 5 times between doing basic science and developing technology. And it's been a really nice spiral, so to speak, because you do a bunch of basic science that kind of shows you what technology might be possible. You build some technology that provides tools that let you figure out more about basic science, and then you kind of iterate that. So I started building Mathematica in 1986, and the first version came out in 1988. And I'm pleased to say that we just had our 35th anniversary, and I was able to take a notebook, Mathematica notebook. We invented this notebook thing back in 1987, which 25 years later, everybody thought was the coolest thing in the world. But there's a lot of other things we invented a long, long time ago that are still probably 50 years from being the coolest thing in the world. But in any case, that was, I was able to take a Mathematica notebook from 1988 on a floppy disk and so on, and I was able to put it into a modern computer, and it just ran. And that was, I thought that was great, because we actually have managed to keep the language compatible over the course of all of those years. And that's partly because, partly I had a trial run in SMP, so I made a lot of the obvious mistakes in SMP and was able to not make those mistakes in building Mathematica and what's now Wolfram language. But in any case, just to sort of continue a little bit that that narrative. I mean, we kind of one of the big ideas, I suppose, of Wolfram language is just this idea that everything is symbolic. You can have, you can have sort of anything. You can. I don't know, what can we make here? Well, let's say we make a random graph or something. Any of these things is just some object that you can treat as a thing that you can work with. So you can compute something from that graph, or I could take, I don't know, I can probably make a. This is always let's see, I can, if my computer, there we go. There's a picture, and we can sort of say, I don't know, we could probably say, let's see, we might have to load up some neural net here, but eventually it'll, okay, it's loading something. It's loading some, oh, there we go. No, I'm not that old. And I'm much happier than that. So, kind of the idea, as I see it, our mission in Wolfram language, different mission from the programming language mission. Our mission is kind of to make a notation for representing things computationally. That is a notation that both computers can read and humans can read. And it's also a thing where our goal is not to make a sort of a sleek, sort of small language. It's to make sort of the biggest thing that contains as much knowledge as possible. So, we can expect that, I don't know, if we say, give me a list of words, it'll know words in English, and we could say something like, take the first letter from all those words and, make a word cloud from those and so on. And kind of the idea is that we have something which is intended for both humans and computers to read, and that's sort of just as mathematics is this kind of notation intended for humans to kind of exchange mathematical knowledge in. And kind of the idea also is that we know about entities, things in the world. I don't know what, I wonder what we know about MIT. Let's see, we may know all kinds of stuff about MIT. It's, okay, all kinds of stuff, all right. But we could also just say something like, take MIT and let's make a picture of something like a geodisk around MIT, let's say, I don't know, a 5-mile disk around MIT or something, and it'll have to load in some data and so on. But this is kind of the goal is to have sort of all of this knowledge of the world built into the language. The goal is this is kind of the notion is make this something where there's sort of computational knowledge built into the language, and the language is a way to express sort of computational things about the world. Well, okay, in my personal trajectory, kind of the next thing that might be of interest, I kind of had been interested since I was a kid in this problem of kind of how do you take sort of knowledge that exists in the world and kind of make it accessible to people. And I kind of imagined that the only way to do that in the end was to make some kind of brain-like AI thing, and that had been what I'd sort of assumed was the case. But as a result of my work in basic science and the new kind of science and so on, I kind of concluded that there wasn't really a bright line between sort of the intelligent and the merely computational. So that meant that I was kind of set up for that sort of philosophical conclusion and scientific conclusion, said it really should be possible to build something where you can just ask it kind of things about the world, and if it's known, then it should be able to answer them. So that's what led to Wolfram Alpha. And I don't know, if we say, something like population of Boston over NYC or something, what its goal is to understand that natural language, convert it into Wolfram language, and then use the computational knowledge we have to try and answer questions about that. Now, I have to say, when we first started building Wolfram Alpha, it was completely unclear that it was going to work. It was completely unclear that we got the right decade or even the right century to make something like this. And I remember taking the team that was working on Wolfram Alpha. We went to do a field trip to a reference library, and it was like, our goal is to, it's a big reference library, our goal is to take everything that's here and make it computational. And we more or less managed to do that. And it's kind of, and the thing that had been difficult in the past had been this kind of natural language understanding. That was one of the impediments. A lot of projects done at MIT actually in connection with kind of question answering, and always the question was, could we make computers understand natural language? One of the difficulties with that was it wasn't clear what it meant to understand natural language. But we had a very definite meaning for that. What it meant to us was, can we take the natural language and convert it to computational language, interpret it as computational language, from which we can then do computations. And so that gave us a definite target for that and let us be pretty successful at doing natural language understanding. Well, in fact, in modern times, so there have been lots of human users of Wolfram Alpha. In modern times, there are an increasing number of AI users of Wolfram Alpha. We built this thing with OpenAI back in March. That's a ChatGPT plugin that calls Wolfram Alpha and actually also Wolfram language to be able to answer questions. Maybe I could show you. No, let me not bother. You can play with it. So in any case, this was something that was sort of made possible by this kind of computational knowledge idea. Well, then another thing that had come out of my physics my new kind of science project and so on, and my whole study of kind of very simple rules can do very complicated things, was, okay, well, I've been interested in fundamental physics, and by the time you see that a rule as simple as this can make something as complicated as this, you start wondering, well, maybe maybe that means that it should be possible to make sort of all the physics out of some very simple computational rule. So I had started looking at that in the 1990s and had made some progress with that. And then about 3 years ago, with a couple of young physicists who told me that I was irresponsible for me not to work on this more seriously, we started looking at this idea, and it turned out it worked amazingly well. And we now, I think, can say that we are pretty certain we know what kind of the machine code of the universe is, and it really is very computational. Let me try and say a few things about that, and I realize I'm, of course, getting short on time, but I want to say a few things about that, partly because one of the things that I think is exciting about that is that the formalism that exists in our physics project is also all a formalism of distributed computing. And so we get to kind of look at, we get to basically take ideas from physics and import them into distributed computing. And I thought I might try and explain a little bit of that to you here today. So first of all, our physics project, let's see, I've probably got a picture here. Okay, let's see. Let me use the other version of this. There we go. Okay, so just how does the universe end up being computational? Well, one of the things that's been long assumed about the world is that space is a continuous kind of thing. It's just something where you put things at different positions in space. Well, that was also, people thought matter was continuous for a long time, and then it became clear, actually rather late, at the beginning of the 20th century, finally people were convinced, yes, water is not a continuous thing, it's made of molecules, it's made of discrete molecules. Also, it turned out light was made of discrete photons. But space, people thought even at that time, space might be discrete, but one couldn't see how that could be made to work. Actually, there's a quote that people keep on sending me from Einstein in 1916, where he said, in the end, space will turn out to be continuous, but we don't yet have the tools necessary to see how that will work. Well, I think now we do, and the sort of starting point of our physics project is the idea that space is made of discrete points. We can think of them as kind of atoms of space. They're just discrete elements that have nothing, there's nothing to say about them other than that they are distinct from each other. And Well, there's one other thing to say, which is that they are related to each other. They have relations to each other. So you can represent those relations by a graph, or actually more conveniently, a hypergraph. And so then in our model of physics, the whole of the universe is just one giant hypergraph. Maybe these days it has 10 to the 400 nodes or something like that. And everything about sort of the physical world as we perceive it is a feature of that hypergraph. It's kind of like, when we have something like an electron, it's kind of a feature of the hypergraph in the same way that something like a vortex might be kind of a feature in a fluid. So, okay, well then, turns out that you can think about, so actually, again, in this people only do a small number of things in their lives type thing, you can kind of think about the transition from this kind of low-level story of atoms of space to the kind of high-level picture of space as being a little bit like those particles bouncing around in the box. When we have kind of a gas, for example, there are all these microscopic motions of particles, and we think that those microscopic motions of particles, when we observe them on a kind of large scale, they kind of aggregate up to things like fluid mechanics. Well, so the question you might ask is, well, what does a system like this, what does this hypergraph with all these rewriting rules and all this kind of thing aggregate up to when on a large scale? The answer turns out to be not the Navier-Stokes equations for fluid mechanics, but Einstein's equations for space-time. So that's pretty cool that you can, from this kind of very low-level structure, you can derive Einstein's equations. It's not something one thought one could derive. And by the way, I might say that the kind of dynamics of the system is just that you are always taking little pieces of this graph and rewriting them with other pieces of this graph. And it's kind of embarrassingly similar to this idea of symbolic expressions and transformations on symbolic expressions. So I didn't realize that until after we developed this model and so on. But in any case, so that's kind of how sort of space-time works. Now, one of the things that happens is we've got these rewriting rules, and one of the features of these rewriting rules is there isn't just one way to do the rewriting. There are many possible ways to do this rewriting. And those different possible ways to do that rewriting represent kind of different possible paths of history. And so what we end up with is this picture where there isn't just one history for the universe, there's lots of branching and merging paths of history for the universe. Well, that might remind one of quantum mechanics, where kind of the essential feature is that instead of sort of throwing a ball and definite things happening, one imagines that there are these many paths of possibilities, and we only get to observe some kind of aggregated version of that. And it turns out that that actually works out very beautifully. There's this thing we call branchial space, the kind of space of sort of quantum branches of possible histories that kind of has a structure that is a little bit like physical space, not really like physical space, it's mathematically different. But it turns out that just as there's kind of laws of motion in physical space related to Einstein's equations and so on, there are laws of motion in branchial space that come from the exact same sort of computational origin. And in branchial space, those laws turn out to be, so far as we can tell, the Feynman path integral. So in other words, quantum mechanics. So it turns out that the nice thing that happens here is that quantum mechanics and general relativity end up being the same theory, but just playing out in different spaces. Okay, why is this relevant? Well, okay, we can look at, let's take a look at something like a trace of the evaluation of an expression. So let's see if I can pull one of these up. We can ask the question. So one thing to understand is we can think of what's happening in this sort of model universe as, what we think is the actual universe actually, as being a series of update events, and they represent events, and they are causally connected to other events. So it's kind of like you've got each event is like the evaluation of a function. It produces some outputs, and those outputs will be consumed by other functions that run later. And those outputs are then, you have this causal graph that represents the relationship between different events, essentially different function calls, that are different evaluations that are happening. So, okay, so you have all these different events going on, and one kind of thing that can happen is you have an event, and it gets consumed by another event, gets consumed by another event. That one can think of as a time-like sequence of events. Those are sequence of events laid out in time. One event causally is necessary for the next event to happen. The other thing that can happen is you've got a bunch of different events, and they're happening in such a way that they're not causally connected. They're things where, if you think about the whole thing as sort of a partially ordered set of events, I have lots of pictures of these I should probably bring up, but oops, that's not what I want. Let's see, let me just find a picture here. It'll be easier to understand if I show you a picture. Let's see. Is that a relevant picture? No, okay. Let me, well, okay, one of these is at least a partial picture. If you look at this picture down here, this is a causal graph, and it has a bunch of, every node is an event. And the big question is, which nodes can you consider to be simultaneous? So nodes that follow each other in a time-like fashion, where one node follows from the previous one, those have to be laid out at successive moments in time, so to speak. But nodes that are not nodes there can be other nodes that could be happening simultaneously. And so the story of kind of what happens with relativity and so on is that what one is doing is taking this causal graph and one is defining simultaneity surfaces. One's defining which events are happening simultaneously, so to speak. Which events are happening, can we think of as happening at the same time? That kind of defines a reference frame that is the way that we define what counts as sort of now in this universe.
Speaking of events and now.
Let me say just a couple more things, and then well, okay. Let me just pull up one or two things here. So the thing that happens is when you do, let's see whether I can find one here. Well, here, let's try this. Let's see whether this does anything interesting. Well, not terribly interesting. Those we can think of as space-like separated evaluations. The succession of things here, those are time-like connected evaluations. And then this is just a table, so it's essentially a list, and it's evaluating three things which are kind of space-like separated. And you can go and do something more elaborate. Let's say we define, let's do this. Let's define a Fibonacci function and recursively, and then we can look at the trace graph of here, and we'll see a bunch of sort of time-like related events and space-like related events. Maybe I can simplify this a bit. Let's see, if I say something like this, I think, let's try this. If we're lucky, that will do something simpler. Okay, so that shows us kind of pieces of the evaluation of that Fibonacci thing. Maybe we make a bigger Fibonacci. And what's relevant about this is we're seeing things which are time-like separated and things which are space-like separated. And we can kind of think of, well, why is that significant for distributed computing? Well, the things that are space-like separated, you can evaluate at the same time on different threads, different cores, whatever. Okay, so that's kind of part of the story. There's much more to the story. What's interesting about thinking about this is that the process of choosing different kind of evaluation models, different evaluation schemes, that turns out to be like picking different reference frames in physics. And there's lots to say about that. But I want to say one last thing about this, which is that I mentioned that in our models of physics, there's this possibility of different branches of history occurring associated with quantum mechanics. The same thing happens here. So in addition to there being space-like and time-like separated events, there can also be branch-like separated events where, for example, one can, in Wolfram language, one can have pattern matching happen in two different ways, for example. And those different branches are they correspond to, so what do they correspond to in distributed computing? Those correspond to sort of, you can think of them as things like different evaluation orders. They represent kind of race conditions and so on. They're kind of a formalism for thinking about how that works. And what's kind of fun is that a lot of the issues that come up in distributed computing map onto issues in quantum mechanics and quantum gravity and so on in a very direct kind of formal way. Well, And by the way, one of the things to understand is that in quantum mechanics, well, one thing that happens in our models of physics and so on is that it's very important that we observers are only able to observe certain coarse-grained aggregated things. That's kind of why we observe physics the way we observe it. And the same is true for quantum mechanics. We're kind of observing, quantum mechanics ends up being this kind of story of how do branching brains perceive a branching universe? How do we aggregate these different branches of history? And anyway, the long story short here, this is, we kind of see why quantum computing is not going to work as advertised, and we also kind of understand why it's hard to do distributed computing. Okay, the last thing I wanted to do, let's be very practical. Okay. Did that work? I think, please, go ahead. We can go on with this. There's more to show here. Yes?
Yeah, sure. I'm curious when we can introspect the space-time graph of pattern matching within the kernel.
Right. The question was about introspecting. Wow, that's introspecting the space-time graph of pattern matching in Wolfram language. Yes, we're working on that. We can do a bunch of versions of that, but it is not trivial when you get these. It's been a long time question of mine to understand kind of the space-time structure of the evaluation process. In fact, here's a thing about sort of personal history. When I was working on SMP, one of the things that I was really concerned with was how the evaluator should work, and when there were multiple things that could happen, which one should it actually pick to do. And fortunately, at that time, I kind of just said, well, let's pick one. And that turned out to be mostly what people want. But actually, the full story of what you pick is a very complicated story. Here, let me show you an example, just for fun. So these are combinators. So people may know about these. They're this thing defined in 1920. So before Turing machines, before all those kinds of things, it's a way of doing computing where basically you just, where's my mouse? Okay, there we go. Where you're just taking these S and K things, they represent symbolic expressions, and it's pretty hard to understand this stuff. You can kind of run it, and I think this is probably adding 2 + 2 or something, and you're representing everything just in terms of these nested SK things. Anyway, the reason I'm showing you this is that one of the things that happens here is that you can see rather clearly the result of different evaluation orders. So, for example, let's see if I can just find one here. Let me see. Maybe this shows one. Okay, there we go. So these are combinator expressions, and they're going to be transformed in some way. And depending on whether you do leftmost, outermost, that is, you have to pick which piece of the tree do you transform first. And you can make, what's sort of interesting here is you can make these things. So, for example, you can make this sort of multi-way graph. This is kind of quantum computation in a sense. You're looking at all possible paths of evaluation here, and you can kind of this is kind of the story of how that works. Anyway, I'm kind of glad that you can get different. In some systems, you always get the same result independent of evaluation order. In some systems, you don't. I'm kind of glad I didn't understand all this stuff back in 1979 because, well, two things were true. Back in 1979, I was working on gauge theories in quantum field theory, and then I was working on all this stuff about evaluation and computational systems and so on. And if you'd asked me, are these two things related? At that time, I would have said, not a chance. These are completely unrelated things. One is about some piece of mathematical physics. The other is about practical computation. Turns out the problem of gauge invariance, the problem of picking gauges, essentially reference frames, things like that, is the same problem as this problem of picking evaluation orders. But I'm glad I didn't know that at that time, because I think I would have kind of frozen in the complexity of the whole thing. Yeah, right. Please.
Yeah. What is a design choice or feature that no symbolic language has taken, but you think would be very interesting for one to do?
Okay. The question was, what is a design choice that no symbolic language has taken, but would be interesting? You know, back when I was building SMP, I was just talking about evaluation orders. I was very interested in this whole question of evaluation orders, and I put these features into SMP for controlling evaluation order. Nobody ever understood how to use them, including me. So, you know, one of the things that would be very interesting is to figure out how to parameterize evaluation orders. So, give you an example. We have, you know, depth-first search. We have breadth-first search. Those are two named ways to kind of traverse something. Okay, but there are a gazillion other ways you can traverse things. Which are the things which are the worthwhile ways to traverse something? Now, you might say, well, people have surely solved this problem. In general relativity, we have this idea of metrics and so on, which are essentially the same idea of, but it turns out in general relativity, we have a bunch of named metrics, the Schwarzschild metric, the Kerr metric, and so on, just as we have, you know, actually there are aspects of the Schwarzschild metric that are very much like depth-first evaluation, where you get to see the whole future of the universe before anything else happens, so to speak. And that's, so you end up with, so that's an example of something where understanding how to parameterize evaluation orders would be very interesting. I've been thinking about it off and on for 40 years, but I think I'm getting close now, finally. Please. Yeah. So like what? Sorry. Yeah, right. So, okay, the question is, are there unique testable predictions of our physics project? There are things that, well, so one of the features of our physics project, when you think the whole of space is made from a big hypergraph, it isn't necessarily three-dimensional. In fact, dimension is an emergent property and a dynamical variable. So one of the things that happens is you get, in that model, the universe starts essentially infinite dimensional and gradually kind of cools down to be three-dimensional. We can't derive the three yet, but cools down at least. So it's likely that dimension fluctuations are left over from the early universe. And so that's one of the absolutely bizarre phenomena, because the mathematics of, you know, Riemann tensors in 3.01 dimensions is simply not known. And I mean, that's something we have to build. But so kind of actually right now, one of the things that's been happening is we're getting closer to actually having predictions. It looks like we have at least one prediction about black hole mergers and gravitational radiation from black hole mergers, which is different. And one of the things that's also sort of interesting is that there's now a kind of a practical code that's been made with hypergraph evaluation that is kind of an alternative way of studying the Einstein equations. So normally, when you study the Einstein equations, you start from these continuum equations, and then you break them down into something discrete that you can then put on a computer. In our models, you start from this thing that is completely discrete, and then you have to kind of build up and hope that you can make it big enough that it shows effectively continuum behavior. You might have to go 10 to the 100 steps, but in fact, it looks like you don't have to go that far to get things which correspond quite well to black hole mergers and so on. And so that's, so right now, I think the most likely thing is probably dimension fluctuations is one thing. You know, what I really want to, you know, back when people were trying to figure out whether water was made of discrete molecules or was continuous, the final giveaway was Brownian motion. Brownian motion had been known for 100 years. People didn't know what it was. Turns out it's molecules kicking little grains from pollen and so on around. So the question is, what's the kind of analog of Brownian motion that reveals the discreteness of space? And my current little guess, I've been studying, actually just recently, I mentioned at the beginning of this that I studied the second law of thermodynamics back when I was a kid. I finally understand, I think, the second law of thermodynamics. In fact, I just published this big book about the second law and the computational foundations of the second law. So studying the second law, I was looking at the history of the second law. Back in the 1800s, people thought heat. What was heat? Heat was a thing that flowed around. It must be a fluid. Okay, so people, and that was kind of because what else could it possibly be? Well, we have a phenomenon like Brownian motion that's 100 years old, which is dark matter. And my current little aphorism is the name of the fluid that was heat was caloric fluid. So my current little aphorism is dark matter is the caloric of our time. In other words, people think it has to be particles because what else could it possibly be? But I suspect it's some feature of the structure of space. But remains to be seen.
Do you have any more Julia demos?
I don't know Julia, so I probably can show you a little bit more. Let me, let's see what I have here. I might have, let's see what I can do here. I think I have a good chance of having, there we go. Maybe I can make, well, basically, here's something maybe interesting. All right, let's do this. Let's start an external session here with Julia, and then let's try to do this. Let's make a function here that's an external function that uses Julia, and I'm going to guess that this function adds 1 to something. Okay, so now let's try running that. So that's now a function. We can just treat that as some, just random Wolfram language function, just like, we could have said, f of x or something here. We can now say ff of something like 100, and hopefully, there we go. Okay, so that plumbing worked. But so that's kind of calling, and this, by the way, in a Wolfram notebook, you can use a bunch of external languages, and Julia is one of them. I think the interesting thing ends up being, and I'm going to kind of guess what you can do here. How do you make a table? Let's see. Let's just try this. I don't know whether this will work. But square brackets. Thank you. Okay, so one of the things that's interesting is data type conversion. I don't know how good it is for Julia. That's something that is quite interesting because you can both get things from external languages, and you can also, in here, you can probably say, let's see if this works. Let's say, I don't know if this will work, but let's say something like this, and that should be, yeah, okay, so that's a little, yeah, okay, so that's running Wolfram language code to inside the Julia, and then running it in Julia and getting the result back into Wolfram language. But I mean, all this stuff, this is sort of the interactive version of that. There's a external evaluate is kind of let's see, if I just say external evaluate, let's see if this works. This might be a little temperamental because it depends on how this, oh no, okay, that worked. The thing that we also have, we've been developing for ages, this very fancy compiler in Wolfram language, and I suspect that there are interesting things that can be done with type declarations that can be transported and so on. The other thing is calling Wolfram language from Julia. There's a pretty elaborate system for doing that from Python, for example, and it's also, we have a really nice way of doing that from C and so on these days. I don't think such a thing exists for Julia. Somebody should build it. That's that, and kind of the thing you get to do. I mean, I think if I find, hold on, I can probably find you just to give a sense of what's possible. Yeah, let me see.
I believe the Julia to Wolfram language thing exists, but it's the older way of doing it, not the latest thing that you guys have now.
Okay. Okay, so the statement is something exists. This is, let me see, I think, I mean, just to show you what one might kind of look for here, let's see what we've got here. My gosh, all kinds of stuff. This is the Python version of this. What's interesting is that you get to actually directly call Wolfram language functions from inside the code. So I wonder what happens here. Okay, there's a WL expr of this thing, and you can then evaluate that. So you get to kind of in a very fine-grained way, kind of essentially treat Wolfram language like a giant library, in this case for Python. It would be cool if that was possible for Julia as well, because then every function that exists in Wolfram language, you will be able to just call as a function from Julia. And if the type conversions, depending on the type, Wolfram language just has symbolic expressions, it's only type, but we have this whole compiler infrastructure which deals with elaborate specifications of types, and that probably would provide a way to transport those to Julia. And it'd be a cool thing to have, I would think. Anyway, any other?
I think on that note, maybe it's time to call things to an end. But if you could stick around and take questions further privately, and maybe come back again, not in 10 years.
20 years. It's been 20 years.
I can't do that.
Yeah. Definitely.
So thanks again.
Social events, the meetup point is not outside, but at the registration desk. Okay, that's number one. And number two, our program isn't over today. We have another mini symposium on the 4th floor at G449, which is to do with radio astronomy and how you can speed up simulations of black holes by 100x.